Hey guys, welcome back to 118C, or welcome back to 118 in general, final class in the series. Whether you're coming from the summer break or from winter break, I hope had a great refreshing break, whichever one you had. Um, last part of the series, let's just get right into it. Hopefully you guys can start strong and end strong. All right, so just get right into it. 118C is going to begin with chapter 19, which is all about the carboxylic acid. Now, when we look at this molecule, and remember 118C being the last part of the series, we have to really think back to the last 2 quarters of material we've, dealt with. But if we look at the carboxylic acid, I think you guys might recognize two key components of it that remind you of the past. One component is this guy here. Hopefully this one is the one that you remember the most, because right at the end of 118B, what is it that we talked about? We talked about ketones and aldehydes. So the carbonyl should be something that kind of sticks out to you from 118B. Okay, and we learned a little bit about the carbonyl, right? For example, just a little bit of a reminder, but the carbonyl is an interesting molecule because it is inherently both a nucleophile and an electrophile. Right, we can see here there is a strong minus charge on the carbon in this bond polarization, where we would expect a little more nucleophilic action. And there is a strong cation character here on the carbon, which we might expect to have a strong electrophile character. Okay, so when we see the carbonyl and the carboxylic acid, we might try to apply this idea that we've seen before. Okay, that maybe there is potentially, right, a delta positive here, or sorry, delta minus there. And there is a delta positive here. Oh, I realize these are the same color. Let's use a different one here. Let's use the darker one. Okay, there we go. So delta minus here and delta positive here, right? So we might try to apply that idea. The other thing you might, notice and remember is, hey, there is an alcohol. And this one, it's okay if you don't remember, it's been such a long time, but this component here, the alcohol, this was back in 118A. Okay, so 118A is when we learned about this guy. And remember, there was quite a bit about the alcohol that we learned, but the important part that I'll remind you of is that alcohols were the system we studied after the alkyl halide, where the alkyl halide was like that perfect, perfect example, perfect, structure to do all those SN2, E2, SN1E1, all that stuff, right? The alkyl halide was the perfect system for that. The alcohol was given as the counterexample, where we can't right off the bat do all those things, but what we can do is we can change the alcohol into something, which I will put the group G here, so it turned into something. And then we could do all those reactions, SN2, E2, SN1, E1. So these things that we are, we've seen in the past, we're going to apply these things again, okay? But we're going to apply them, cumulatively onto the carboxylic acid. And I think the best place to start is, let's talk about that sort of alcohol character first. So just a little bit of a reminder, back in 118A, right, again, one thing we talked about was, hey, alcohols have that really weird reactivity where if I try to do an SN2 reaction straight up, so you might remember sodium nitrile, DMSO, that was like, if I did this with an alkyl halide, it would work. This reaction would not work at all, because if you try to do this SN2, what you're going to be doing is trying to kick off that alcohol there, and that's just not going to work, right? Because OH minus is a terrible leaving group, terrible, terrible, terrible. So we're not going to be able to do that, right? So a weakly basic, you might remember that term, weakly basic. A weakly basic nucleophile really didn't do much of anything. On the other hand, let's say I use something a little bit stronger. For example, let's say that I try to use an alkoxide or an alcohol, right, that was deprotonated. This type of reaction could be an SN2 or an E2, because again, we're using a strongly basic nucleophile now. And again, we don't really expect to see either E2 or SN2 because OH is a bad leaving group, but we do actually see a reaction here. We see a reaction that the proton has been removed from the alcohol. So actually, let me make this a little bit different. Let me make it this isopropyl alkoxide. But this guy actually did do a reaction. It took off the proton. So OHs are particularly acidic bonds. And remember, the acidity of this was around 15. So this reaction here is sort of an NR, so we can kind of ignore it. But in alcohols, we did see one type of reaction that could occur, and that was acidity, right? An acid-base reaction. So we can actually pull off this proton here. Okay, we can pull off this proton here, but it takes, a pretty good base, right? This is a pKa of 15, which means that only things that are above 15 will pull this proton off. So what are some good examples of that? Very good example is NaNH2 minus, which has a pKa around 35. NaH, so sodium hydride, pKa around 30, 35. What's another good example of something above 15? So you don't necessarily have to be completely above 18. So actually tert-butanol or tert-butoxide is above 15. It's at about 18, but NaOH will also work. It'll be just a little more of an equilibrium because it's about the same pKa, 15, 16-ish. NaOH will deprotonate this, but it'll be more equilibrated. These are more complete deprotonations. These guys will completely deprotonate an alcohol. This one, not so much. Okay. Butyllithium, right? Carbon acid. Carbon acid is 100% going to pull this off. That's a pKa of 50, right? So these are a couple of bases you should have in mind that could, pull off a proton particularly easily off of an alcohol. Okay, and again, that value we set on that, right? How much can this oxygen stabilize this lone pair? The value is 15. Now, not only can we, take a proton off, so have the alcohol act as an acid, but remember, alcohols also have these lone pairs here. And these lone pairs could act as a base and pick up a proton, right? This is all the way back in 118A, right? The concept that anything with lone pair has the ability to act as a Lewis base, okay? The ability to act as a Lewis base or a Bronsted base, depending on what definition you want to use, okay? And so the result of that would be this structure here, OH2 plus. And so again, this here, the ability to take a proton and become positive, oxygen's an electronegative atom, doesn't want to be positive. So this is a pretty low number, it's -1. And what that signifies to you is that it takes some pretty strong acids to do this. Namely the HXs, would do this. H2SO4 would do this. H3PO4 probably would do this, right? You need something sufficiently acidic to get that on there. Really deeply acidic conditions are what going to protonate this alcohol. Okay, so again, a little bit of a reminder of what we've done in the past, right, with alcohols, so that when we look at the carboxylic acid, we can apply a little bit of those same ideas. Because if you look, really, this is still some kind of OH, right? This here is still an OH where an oxygen could, give up a proton. So let's say that this oxygen did give up this proton. What do we end up with? We end up with an O minus. Okay, and again, the same way that this O minus was particularly stable because oxygen's electronegative, so is this one. But there's another quality about this O minus that's also really good as well. And you have to, remember that whenever a charge, right, or electrons are next to a pi bond, right, what can those electrons do? So when electrons are next to pi bonds, what can they do? Right, answer that to yourself real quickly, right? They can resonate. And so we can actually have equivalent resonance forms, okay, of the carboxylate anion. And so this anion here is, if being on one oxygen is stable, imagine how being on two oxygens, how stable that is. It's really, really stable. The value we give this is a pK of 5. So look at that 10-unit drop. So what that means then is that all of these things here that we've already named can, deprotonate a carboxylic acid, right? So these things for sure can pull off that proton. I can actually even annotate this to RO minus because RO minus will just do it. They're at 15, right? 15 can definitely deprotonate 5. Okay, NaOH definitely can deprotonate 5. N-butyllithium, in what world is N-butyllithium not deprotonating 5? But we have to add in a couple more of these guys. Okay, we're gonna have to add in a few because 5 gives us 10 extra pK units to have, as a leeway. But there's things that can deprotonate an carboxylic acid that can't deprotonate an alcohol, and one of those things is going to be amines, neutral amines. Now, this might be a really weird and foreign concept, and that's okay. That's totally okay. But amines tend to have a pKa around 9 when they're aniliniums. So, or sorry, ammoniums is what I meant to say. So what do I mean by that? I mean NH4 plus. Okay, NH4 plus is a great acid, or sorry, it's a result of a great of a great acid with an amine, and 5 is considered a great acid in front of this amine here. Okay, so all types of amines have the ability to be protonated okay, because they're all going to be around 9. All you guys are gonna, it's like 9 to 11. Okay, that's the range for these molecules here. And we're going to have to remember that, right? Just as we're going to have to remember a couple of these. So I'm going to put stars next to some of these. You might want to remember this one, and definitely want to remember this one, right? Right in your notes, right? Amines and alcohols, right, and hydroxides, they really are going to be pulling off those protons off these carboxylic acids really, really easily. And again, it's just that the fact that there's 2 oxygens here that are resonating. Now, one thing you might remember from 118b, and it's okay if you don't, right? It should be no surprise to you guys that the carboxylate anion is very stable, because maybe when I draw it like this, you guys might notice something here, right? Do you guys notice something familiar about this system when I draw it like this? Maybe not, maybe not. So what I'll do is this, but what if I did this? What does that remind you of, this system? If it doesn't remind you of anything, that's totally okay, but I'll just remind you, this is the same as an allylic system. And we talked all about in 118b for midterm 2, why allylic systems are so stable. Those same things are at play in the carboxylic acid, in the carboxylate. So the carboxylate is super, super stable. Even the orbitals are stable, right? Even the orbital energies are lower, right? Because of the mixing of those p orbitals. Okay. And again, as we talked about with the alcohol, right, there is going to be electrons on this oxygen here, right, that could potentially act basic. Well, actually, there's 2 pairs of electrons that could act basic here, right? There's also these guys too. Now, we didn't really talk about it, but we could for a second. We know that carbonyls can act as bases, right? They can pick up protons. We've seen that. That's how we activated our carbonyls in acidic conditions for attack, right? Well, we've also done that here too, right? So we've seen that, hey, this value here to go from here to here is pretty low. It's about negative 5-ish, or negative, it's a good value. Negative 5 is probably a good value, right? So negative 5-ish. But alcohols can also do it too. And if we go by values, it looks like the alcohol is more basic. Okay, so how can we choose? How do we know what to choose, to act as the base? And really the only way to know is, hey, just protonate both and let's see what happens. So let's see what happens when this guy takes a proton. Let's see what happens when this guy takes a proton, right? What is going to result? And so one system will look like this. Okay, this is that burgundy color, protonated, and one system will look like this. Now take a second and try it yourself, but try to read. Hello. Sorry, mic is bad, so it's going to go out a couple times. I apologize. But I'll give you a little bit of a hint here. Try to use the reason that we use for why this is stable, right? What made this minus charge more stable than this minus charge? And maybe try to find that thing, what was here. Find that thing here. Which one has that thing? Okay, so that's my hint to you. So try on your own. And hopefully you realize what I was alluding to is the fact that this is resonance, right? So this, I should have mentioned, these are equivalent structures. Okay, these are equivalent structures. Okay, and what we're looking for is resonance, right? One of these two is going to resonate. It's going to make it the whole lot better. Okay, so when I look here, right, and I think of resonance, really all I think of is maybe this bond polarizes here. But when I do that, I kind of notice that I just make a jungle of charges here. Um, and nothing really resonate, right? If you think about it, right? Like this oxygen does have a lone pair, but how's that going to resonate? If it did, let's say this lone pair resonated. If it did, you're forming a 2+ species. And if there's one thing you should hopefully remember from 118A, 2+ will never exist. They're too unstable. Please don't ever make them. So this one probably can't resonate. So we are already thinking that maybe this one's not good. But if I look at this one, right, and I think about the lone pair on this guy, right, that could move here, which pushes this guy here. Look at that. This guy resonates very easily. And not only does it resonate, look at that. It forms equivalent structures, right? I know it's a little flipped over, but this is exactly the same. These two are the same. Both have a carbonyl protonated, both have an alcohol not protonated. And so that same equivalent structure is going to make its way back, right? And now we know, hey, this is never going to happen. This is never going to happen because of resonance, okay? Because of resonance. Now, it's not a very easy thing to do, right? As you can see, I wrote the value there. Okay. But in terms of the two things, right, or the two oxygens, sorry, that could get protonated, it's clearly going to be the carbonyl. Okay. So while the carboxylic acid acts as an acid on the alcohol component, it acts as a base on the carbonyl component. So it's a little bit of both. It's like both a base and an acid. Now, again, it's more of an acid than it is a base. Its basicity is -5, which is not a good basic number, right? That's not a good number at all. So it's going to be very, very hard to do so. Again, we're going to really need those very strong acids. So HX, H2SO4 kind of thing, right? But that's totally okay, right? Because these are acids you guys are used to using anyways. Now, again, just to prime it in your brains again, right? Really, this acidic part is not going to be too big of an issue, right? You kind of just give the carboxylic acid proton, it protonates, it activates, and you can think about how proton helped you guys back in 118B with the carbonyls, right? Like what did protonating the carbonyl do when you protonated a ketone and an aldehyde? It really just helped you out. But really, it's this basicity here that's going to be interesting because, again, remember, these guys, we're going to come back to them, right? We're going to be using them in this section, but we're going to see how these guys are kind of a little bit weird in the way that they react. Okay, because remember, this proton, as being an acidic proton, is going to want to go first. Remember, acid base is always faster than any other reaction. Okay, so if there's an acid base that can happen, it will, and it will be the first thing to occur in the reaction. And sometimes that is enough to stop any reaction that you wanted to occur. If that doesn't make sense, so don't worry. We're going to be going over this way more in depth as we move on. Okay, cool. So in the same way that, oxygens have extra things that can stabilize them, for example, um, the fact that I could put chlorines here, right? And that would make this alcohol more acidic than this one. We have the same sort of effect with carboxylic acids. I can make trichloroacetic acid here, and that will always be way more more acidic than carboxylic acids. It turns out actually, if we give this a value of 5, some of these trihaloacetic acids can drop all the way down to like 1. That's how strong this effect is on this proton. A little bit of a reminder, how does this effect work? Well, we know that halogens are electronegative, so they steal electron density. So this carbon becomes positive, right? So this carbon here becomes delta positive. Right? If that carbon becomes delta positive, it starts to pull on its neighbor carbons. That makes those neighbor carbons delta positive, right? And this is already delta positive, so it's going to be even higher delta positive. And again, carbons that are delta positive are just going to start pulling on their bonds. Even this carbon-oxygen bond is going to be pulled on by carbon, even though it's going to lose it. And so the net result is that we're going to see a dipole forming on the oxygen hydrogen bond, where the electrons are going to pull closer to the oxygen nuclei. Now, two things are resulting from that. One, the electrons being pulled closer to the nuclei makes them more stable. And two, that enhances the delta minus, delta positive character of the OH bond. And if the H is higher if the H is a higher delta positive, that means it is more acidic. So a little bit of reminder of the inductive effect, right? Now, when we are comparing of the same distance, right? So for example, acetic acid to acetic acid, just keep in mind that electronegativity is what dictates acidity strength, right? So the fact that these are bromines and they're comparing them against chlorines at the same distance from the H, right? So like 1, 2, 3 bonds, or sorry, 1, 2, yeah, 1, 2, 3 bonds, 1, 2, 3 bonds, right? All these are 3 bonds away from the H, right? The distance is the same. My point there. We would just do it by electronegativity. You can also compare by distance if they're the same halogen. Just remember that the closer these guys are, the more prominent their effect. So acetic acid or trichloroacetic acid is always more acidic than trichloropropyl acid. Okay, propyl acid. It's always way more acidic. The reason just being, right, like these dipoles, the sigma effect here is they're not. It's not a physical movement of electrons really across atoms. It's like bond polarizations, pulling of electrons. The more of these that you have to form, right, the weaker the effect is overall. So you can actually even almost do it this way if you'd like. You can think of it as it gets to like dots at this point. And then it gets a little bit better and better and better, right? Like it's weaker as we get to this point, but you know, if we're closer, the dots aren't as prominent. It's like a lot more stronger, this effect. Okay. Now to kind of summarize this effect in a way, right? What we're essentially looking at here is, again, if this carbon here has to be delta positive, right? What we're basically saying is that if we had some entity on this carbon, right? This entity, this has to be positive and acidity goes up. So when there is a cation that's located right on this carbon here, right? So we can have, I'm going to make this smaller, right? Let's just say that there is a cation of some kind here, right? The acidity is going to go up a whole lot. Another way of saying this is that basicity goes a lot down. The opposite would hold true as well, right? That if there's a minus here, then acidity will go down, right? Because that's electron-electron clash, and that's not what we want. But basicity would go up, okay? This is essentially what we're saying when we're saying that the inductive effect is a good effect, right? Because we need something that's going to pull electrons, right? Cations are great electron pullers, whereas some kind of minus charge, some kind of donating group, right? It's not really going to do that. It's really just going to push electrons, right? It's going to push electrons in. That's really bad because we don't want electrons close to our electrons. We want them far away. Okay. What I'm essentially getting to with this is that, you know, there is a group of molecules we've learned about in 118b where we can influence the whole group to be positive or negative. Essentially what I'm getting at is benzoic acids, right? Because we did learn how to influence the positivity and negativity of a benzene, right? We can add some group here or some group here, right? Actually, let me put it over up here. We can influence what group we have either here or here, right, to match the effect that we're seeing here. So maybe even if you have to look back in your notes, but take 1 second to think about, do you remember what those kind of groups are? If you don't, it's okay, I'll just tell you. Electron withdrawing groups increase positivity and electron donating groups increase negativity. And so we can see already a little bit of a trend that electron withdrawing groups will increase acidity. Okay, so these groups here will increase acidity, right? Whereas EDG groups will increase basicity instead. So already we have a little bit of an idea what to expect going into the full explanation of what EWG and EDG will do. Okay, oops, sorry. All right, let me put my phone on do not disturb. Apologize. Okay, so let's talk about EWG first, although we'll talk about both of them, don't worry. Let's talk about EWG and think about what effect EWG has on the rings. Now, just a little bit of a primer, Okay, so to sort of get you guys to start seeing things, if there is, actually doesn't have to be in carbonyl, it could be any group here. If there is any group on a benzene ring that has the ability to have a resonance effect, so let's put here resonance effects. Something that we'll come to notice is that those resonance effects will be primarily prominent on the ortho and para carbons. So if a group has any effect, ortho to that group and para to that group, there will be some effects. Okay, and that effect will be just determined by whether it's an electron withdrawing group or an electron donating group. Okay, so think about what we talked about on the last page. What do you think what that effect is, right? Spoiler alert, it is whether it's a minus charge or a positive charge. Okay, a little bit also of a little reminder here. I'm going to put ortho para together in these examples. The reason for that is because if you remember, if a group is ortho or para, they have the exact same resonance forms. Okay, ortho and para share that they have the exact same resonance forms. So I'm not going to draw out para on its own when I can just put ortho and para together. Okay, but when I draw the resonance forms for these guys, right? So I'm going to use a very traditional electron withdrawing group and use NO2. I'm going to show for both ortho and para, even though this is ortho. So keep that in mind. Although this is ortho, ortho and para are both going to have the same resonance forms. Okay, cool. And then we'll have meta have its own, because again, meta is going to be different. Okay, so let's look at the ortho-para effects first, right? What does ortho-para do? And actually for this first resonance form, we are going to draw NO2. Okay. Because again, as an electron withdrawing group, what does it do? It withdraws electrons. So these electrons here, we're going to say, are going to go here. Okay, and we'll push them in like that. So you can think of it sort of as an electron vacuum, if you want to. I like to call it a Dyson electron master. Okay, because it's, sucking up electrons like a Dyson. Dyson is a, I think it's a vacuum, whatever. Anyways, it's fine. But this is what we would probably expect first. I'm going to go back to abbreviating this to NO2. Okay. Oh, actually, it'd be NO2 minus. Because you'd add a cation. Oh, there should already be a cation here. Forgot about that. And we're adding a minus charge. Yeah, it should be NO2 minus. Okay. And so what we'll see, oops, sorry, cation in the wrong spot. Right. What we'll see again is I want you to notice that thing that I mentioned. If a group has some effect, that effect should be ortho and para. And we can see already it is having an effect ortho to the NO2. So let's move that there. Where does that put the effect now, right? Where is the effect now in relation to NO2? Right, where would you guys put that effect? That effect should be now para to NO2. We'll draw one more form here. All right, there we go. And once again, right, look at that. If a group has some effect, it's going to be ortho and para. And what do we notice? Look at that. Ortho, para, ortho, right? That's where we see the effects. Okay, so you can kind of, if you want, you can get a little bit ahead of me here and try out, on meta where the charges will go. But what I want you guys to focus on is look at where the cation is, right? It's in the ring, which makes the ring overall positive, which is good. But notice how on this particular resonance form here, notice how that positive is right underneath the carboxylic acid. Now, where did we say we wanted that cation, right? To make the carboxylic acid more acidic, right? Remember, we wanted it right next door. And that's exactly where we see it in this resonance form. It is right next door. It is, I like to say underneath because it's like literally underneath it. But when it's, adjacent to it, when it's on that alpha carbon, and that cation is alpha to the carboxylic acid, this is a great resonance form for acidity. And we favor it a lot. Okay, this is a very good one. Okay, and so you can imagine that orthopara acids, electron withdrawing acids, are going to be very, very, very acidic. Okay, especially with an NO2 group. You should remember NO2 is super, super withdrawing. Now, if we apply that same logic onto the meta, right, we draw all these forms out. And I keep drawing this in again. Now, for those of you that wanted to get ahead of me, or maybe you didn't, maybe you stuck around, right? I'll ask you now, right? What do you notice about the cation, right? First off, in terms of the group effect, right? Does our group effect make sense, right? Do we see what we predicted with the group effects for resonance? And the answer should be yes, right? Because again, ortho. Oh, sorry, I redrew the same resonance form. It happens. It's okay. That's what I wanted. There we go. Again, what do you notice, right? What do you see? And hopefully what you see is, yeah, we see that ortho-para pattern, right? Ortho-para. That chart is ortho-para to that group that's causing the effect, right? So that's one thing hopefully you notice. But what about this? Do you notice that, do we have this resonance form here that's really good? And the answer is no. The answer is no. We do have a cation on every single ring, so that's very good. Okay, but we do not have the cation ever alpha to the carboxylic acid. We never have it here on this carbon, right? You can see that in all of them. It never happens. So what that means is that meta has no resonance effect. It has no resonance effect. It only has an inductive effect, if it has any effect. Okay, and what does inductive effect mean, right? Well, remember that NO2, while it does withdraw via, the pi framework, so it does withdraw via resonance, which is a pi system, right? So resonance is a pi system. We can also have inductive effects, okay? Inductive effects. And what did we talk about for inductive effect on the last page? If there is an inductive effect, right, it gets stronger and stronger the closer we are, right, to the group. It's stronger and stronger the closer we are to the group. Let me draw this a little bit more better. Okay, so hopefully what I'm trying to show here is the farther we are, the minuscule the effect is. The closer we are, the better it is. Okay, and this is a sigma effect. Okay, so when we look at the meta group, right? Yeah, meta is not as close as ortho, but it's also not as far as para. And so we still have the availability of an inductive effect. And that inductive effect is what is going to explain why meta is still an acidic benzoic acid. Okay, but remember, inductive effect, a sigma framework, right? That is going to be a weaker effect than resonance. Resonance is always stronger. Inductive is always weaker. And so because of that, ortho and para are always going to be stronger acids, right? They're always going to be stronger acids than meta. So when we're comparing ortho and para, what do you guys think is going to be the stronger one? right? One thing I'll tell you before you try to answer this yourself is that we can't use a resonance argument because we just said ortho and para have the same resonance forms. So resonance cannot be the reason for why ortho or para is the stronger acid, right? So what other reason could we possibly use if we can't use resonance, right? If you need a little bit of a push, a little bit of a hint, right? How did we explain meta acidity and how can we apply that to ortho versus para acidity? If we can't use resonance, we have to use induction because inductive effect, it's not like meta is the only thing with an inductive effect. Ortho and para have it too. It also has it too. And so all we have to do is just think, right, in terms of inductive effect, if there was an NO2 here versus an NO2 here, who has the better inductive effect, right? Who has the better inductive effect? Who is closer or farther, right? Inductive effect is better the closer you are. And in terms of ortho and para, ortho is the closest you can be. Ortho is going to be the stronger acid simply because it has the better inductive effect. Okay, so it's like a ortho and para have a combination of both, which makes them better than meta. But ortho has the stronger combination of both. Okay, and that's how we explain EWG. Okay. Now, again, I want to stress this, right? What we've covered right now is the resonance effects, right, of resonance withdrawers, right? These, this order here is truly, I would like to say, sort of a resonance-driven order, okay? When we order everything at the very end of this acidity point, maybe that statement will make a little more sense, but when we're thinking of, ortho para meta, truly what we're thinking about is resonance withdrawing EWG. So I'll even put here that currently what we're talking about is resonance EWGs, okay? Hopefully that'll make a little more sense at the end why I'm making this distinction now, okay? When it comes to EDGs, and again, we're really primarily focused on the resonance EDGs, we're gonna do the exact same thing, okay? And once again, I'm gonna say, hey, this is probably a great time to get ahead of me here, right? And try to draw these resonance forms on your own. I'm going to use OCH3 because that's a great group to use. But I would really like it if you guys try to get ahead of me here, right? Think if there is going to be resonance effects in either of these, right? Like we've shown here, do you guys think it's going to be different from these resonance forms? So do you guys think these resonance forms are different? The answer is kind of yes and no, right? Because in one way, they are completely the same in that the electron movement, the fact that there is going to be a resonance effect ortho and para is going to be exactly the same. So a little bit of elaboration, right? When an EDG donates, okay, when an EDG donates, right, into the system as such, right, I should expect the exact same resonance forms as above. But what's going to be different? What's going to be different about these resonance forms? They can't be exactly the same, otherwise everything would have the same acidity, right? What is the difference in the resonance forms? If electron withdrawing causes cations, electron donation should cause anions, okay? It should cause anions. So that's going to be the major difference here. But hopefully, if you're getting, again, as always, I always encourage you guys, try to move a little bit ahead of me to see if your ideas are the same as my ideas. It's okay if they're not. But hopefully you can see here how the electrons are moving exactly the same. The only real difference is what overall charge do we see in the ring. Okay, so that's what we see for ortho-para resonance forms. And again, remember how we had this resonance form here? Remember how we had that? And we mentioned right? We mentioned how when there's a charge alpha to the carboxylic acid, there's an intense effect. Well, if before there was a cation and we said that was good for acidity, have a cation. Now we have an anion. What do we say for that for acidity, right? What do we say for that? We said that it would be not very good because acidity goes down and basicity will go up. So this here is going to be our unfavorable resonance form. So unfavor, and this is bad, right? High energy resonance form. And so this is why back in 118A, I make such a big gripe when professors teach you guys like that there's minor and major resonance forms, because, you know, in my opinion, right, every resonance form contributes to some extent. So you should consider, you know, what it does to the overall hybrid of the molecule, right? And in this case, I think it's so important to realize that, hey, right, all of these resonance forms here, even the high energy ones that don't exist for very long, have such a prominent effect, right, on the overall chemistry we're seeing here, right? This high energy intermediate in the orthopara electron with electron donating benzoic acids is completely the reason why electron donating groups that are orthopara are the weakest benzoic acids. Okay, these guys are the weakest benzoic acids all, you know, overall. And again, 118C is the culmination of all of OChem. So hopefully, you know, everything you guys have been learning up until this point, you can now start to synthesize all together. Okay. One final resonance form, and then we'll be free. You know, by the end of this video, if you're taking notes along with me, we should have really, really toned. This is a really great forearm exercise, I would say. If drawing for a whole year has taught me anything, it's that your forearms really feel it. Actually, if there's any artists that hear me say this, and like, let's say that what I'm saying is not something that I should be feeling, like I'm not supposed to be having this forearm workout, please let me know what I should be doing to prevent this gruesome forearm workout. Cool. Anyways, back on topic. Again, when we look at these resonance forms, right, between orthopara and meta, before orthopara was great because that positive charge put that charge underneath and we were really happy. But now there's a minus charge underneath that's very bad. So orthopara are just going to be very bad in terms of acids, right? Meta just wins by default because, yeah, there's a negative, but that negative doesn't ever become alpha to the carboxylic acid. And so because of that, the meta group is just better. Okay, so the meta group is just better. Okay, again, if there is a resonance effect in orthopara, then the only thing in meta is going to be what effect? What effect is there going to be in meta? Now you might have hesitated because you're thinking, well, wait, oh, I know a withdrawing group would have an inductive effect, but what about OCH3? And the answer is, although OCH3 is resonance donating, it is also inductively withdrawing because, you know, inherent to oxygen is that it's an electronegative atom, right? That's something we do know. That's something we learned back in 118A. And so even though oxygen has a stronger donating effect, that doesn't mean that it's, you know, withdrawing effect, you know, that's by induction is like completely just gone. It's still there. And so pretty much every group, both electron withdrawing and electron donating, have some level of induction. The only group that doesn't is R groups. Actually, it might be worth our while to go over what is an electron withdrawing and electron donating group again. Okay, so I'll dedicate a page to that. Okay, but again, if we think about, you know, meta versus orthopara, meta has a good inductive effect, whereas orthopara have a bad resonance effect. And then once again, how do we determine whether ortho or para is better? Well, hey, what was that one effect that they also have that we can compare between ortho and para? It's going to be the inductive effect, okay? And once again, ortho is closer than para. So the inductive effect is a lot better and it's withdrawing. So ortho ends up being the better acid than para. Okay. Now we have a mop. All we need now is a bucket. I apologize. I know that was a really bad joke, but hey, it was there. I had to, I had to take it. You guys would have done it too. You guys would have taken that joke too. Okay. Cool. So hopefully now it makes a little more sense, right? What we're looking for in orthopara, in electron withdrawing and electron donating benzoic acids. Okay. And so we can kind of culminate all of this onto a single page, right? Where, again, who are the most acidic benzoic acids? Those are always going to be the electron withdrawing groups. And ortho is always better than para. Okay, because they both have a resonance effect that's really good. It's just that ortho is closer, so its inductive effect is a lot better. Now meta is not terrible, but it only has an inductive effect, and resonance effects are always stronger, so we really need that resonance effect. Now again, if we think about EDG, right? EDG is trying to prevent those resonance forms that put a charge underneath the carboxylic acid. And so meta is going to be the best position if we want an acidic donating group. After that, then we have ortho and para, where again, ortho and para are just bad because they have bad resonance effects, but there is still an inductive effect alive. So the ortho acids tend to be better than the para acids. And so this is a very good generic trend that we see for resonance withdrawing and resonance donating groups. Okay. And so just a little bit of a reminder, right? What is an EWG, right? What is that? That's like NO2, CN, a carbonyl. I remember in your 118 notes, Nasiri has like a larger list and they're ordered in their strength. So you can by all means use that list to help you out and figure out, right? What is a stronger activator or, what is a stronger deactivator, right? Like what is the order of them? Just trying to think who else is a resonance withdrawing group. Yeah, so I would definitely consult that list in your notes. It's like chapter 16 notes, I think. But this is all I can remember for now. And these are the resonance guys. So all those effects that we talked about are prominent here. These guys here are going to be the inductive electron withdrawing groups, meaning they have no resonance effects whatsoever. They only have inductive effects. And because of that, their rules are going to be slightly different. Okay. What I mean by that their rules are slightly different, is that when we think of inductive groups, so if there's only an inductive effect, what that means then is that the only thing then is the distance of the group from the acid. That's the only thing that's going to influence whether it is a good acid or bad acid. So I'll use CF3 here, but CF3 being only inductive means that the order goes ortho, meta, and then para, because there's no resonance effect, right? If there's no resonance effect available, right? If you can't have resonance as a component of the reaction, or sorry, of the ring affecting the acidity, then you can't really use the ortho para meta orientation, right? Ortho para meta. It has to be ortho meta para, because these are only acting by how close the group is. And so these are the three guys that will do that. Okay. On the other hand, we have EDGs. And for the most part, all the EDGs are pretty much resonance EDGs. Okay. And so you guys might remember these very, very well. Remember, NR2 with a lone pair is so different from NR3 plus. Hello, sorry about that. NR3 plus is so different from NR2 with the lone pair. Please do not confuse them. Okay, but these are some groups. I have not ordered these by the way in strength because I don't remember that order, but these are pretty close. Right, you can again look on that chart that Nasiri gave you guys. There's only one inductive like EDG, and that's R groups, but these guys are so weak. All carbon or all R group benzoic acids are equal. So what do I mean when I say this? I'm gonna just draw it in a very lazy way. But if this were R, R, or R here, all of these are equal. These guys are equal in acidity. R groups have very minimal donating power. They're the weakest donator on the planet. They don't really do much difference to each other. So if you had to order them, I think even Dr. Nasiri said herself, if you had to order these, you would order them as the same number. You can't really put them opposite. Or you can't really put any, like you can't put like 1, 2, or 3 on them. They're always all 1 or 2 or 3. Point being, they're all the same. But yeah, so if you ever see these guys, they're weakest activators, but there's really no difference between the order of them. Okay, but these are the guys that we have. And again, remember, all these guys here, they not only have a resonance with donating group or resonance donating effect, they have an inductive withdrawal effect too. Okay, so pretty much these EWGs and these EDGs, right? All the EWGs and EDGs of resonance have this group effect and they have this inductive effect. Okay, it's only those under the inductive category that are only inductively active, right? So only inductive, only inductive. Now, these guys here, depending on what they are, if it's the bromines are the weakest deactivator. So the bromines would go here if they had to go somewhere, or the halogens, I should say, really. So the halogens, if we had to put them somewhere, they go here, and you order them, like if you had to order them within themselves, it's just by electronegativity. So F is a better acid than Cl, which is better than Br, which is better than I. Okay, that's just by electronegativity. How likely or how how much can it pull on that carbon bond? Like how strong can it make its inductive effect? CF3 and NR3 are like the best deactivators. So depending on the identity of whatever the other EDVGs are, typically CF3 and NR3 and NO2, all those guys are over here, right? I think nitrile also kind of goes over here too, but you get my point. It will depend, right? Where do I put CF3 and NR3? It will literally depend on what the other groups are, right? Like if this is CF3 and this is like, I don't know, like BR, clearly BR or CF3 is going to go here, BR is going to go here. I think NO2 is the only thing stronger than CF3. So even if CF3 were, were here, but this were NO2, NO2 acid is going to be stronger because NO2 is just a stronger withdrawing group. I'm pretty sure that's the case. Again, it's going to depend on the order on that one notes. Okay. So yeah, now, again, the reason why we were able to always put this here is because they're the weakest deactivator. So if they're the weakest deactivator, they should always be on that line between deactivator and activator. Okay, so that's how we get X there very, very easily, right? So that's where X would go. Write this down because I'm going to erase it real quick to show you guys another trend. Okay, actually, I guess I don't have to. I can just leave this here. So EWG. I'll just put that this is an EWG, right? That's where X would go always. It's always the weakest one, right? One last thing that we should be comfortable with ordering is the actual just benzoic acid itself. So a plain benzoic acid. Where would you guys put this? So try to put this on this map on your own. It actually might be easier if we get rid of the X real quick, right? And we just kind of do it from here. Where would you put it, right? So try this on your own. Where would you put it? I'm willing to bet Acyl Halide that a lot of you guys put it here, right, between EWG and EDG, and I think that's a great place to put it, right? Like it's very safe. you're really confident that that could be an answer. And I'll be honest, when I first used to do these problems, I used to do the same thing too, that it would go there. But you have to keep in mind, right, that a benzoic acid has no effect, no resonance, no inductive effect. What I'm trying to get at here is that there is no good effects, no effects on this ring at all that could increase acidity. Why is it important that I'm bringing that up? Because this guy here has inductive and withdrawing effects that are good. Sorry, inductive and resonant effects that are good. So two checks, resonance and inductive effect. This guy only has inductive effect. Although it feels very safe to put this here, remember that even though EDG donates, EDG still has a good inductive effect. So the fact that it has a good inductive effect, although it has a little bit of a bad effect, right, means that being the only EDG ring with a good effect, right, overall a good effect, it is actually going to be more acidic than a normal benzoic acid. Okay, and you can even look this up if you like, right? You can look up the different so these are methoxy benzoic acids. You can see it in methoxy benzoic acids very, very clearly. Okay, methoxy benzoic acids are way more acidic than benzoic acids, because remember, as long as there's no negative charge here, there is no really bad resonance effect. Okay, there is still a good inductive effect, and this inductive effect is still better than having no effect whatsoever. So in reality, benzoic acids will always go after meta-directed EDGs, or a meta-placed EDGs is really what I should say, right? So if it's a meta EDG to a benzoic acid, this is where it's going to go. I'm going to replace this. And remember, we said that X would probably go here because it's the weakest deactivator of them all. Okay, so this should help you out in about 95% of cases. I like to keep, an error of 5%. But really, what I want you guys to take from this is think about the effect occurring on the ring, right? Or the effect occurring on the benzoic acid. Are there resonance effects? Are there inductive effects? That's really what you really want to take into account. In the past, there have been questions where Dr. Nassiri has thrown in, like, for example, this here, right? And asked you to compare it to like this here. And a lot of people get stumped because they're like, wait a minute, I know how to order benzoic acids, but how do I order cyclohexanes? Don't freak out, right? Think about it. What effects are present, right? We know for benzoic acids, there is actually, let me make this one different, right? Let's make it this one here. We can actually talk about the meta one too, but I think the point I want to make is better made with this here, right? With the para, or an ortho one would have been good too. But we know that there is a resonance effect and that there is an inductive effect if there had to be one in a benzoic acid, right? Because benzoic acids are altered by resonance and by induction. If I look at the cyclohexane, do you guys think that there's any resonance available in the system like there is here? No, right? There is no resonance available because there's no resonance, there's no pi bonds, right? The pi bonds are gone. Resonance is no longer something we can consider. So these guys are automatically way worse than everything, than any of these guys, because there's no resonance. Now there could be a bit of an inductive effect, right? But that's the only thing it has going for it, is an inductive effect. In general, inductively active cyclohexanes are just worse than benzoic acids in general. Okay. And so again, we could also think about if this were meta, right? We could also think about if this were meta. And you might be wondering, like, like this is meta. Oh, oops, why did I draw this in here? There is no resonance effect, right? So resonance effect here is not that great, right? And there is an inductive effect, but this is the same thing, no resonance effect, and the inductive effect is good here too. Well, then which one do I want to go with, right? Which one do I think is better? And, I'll say a good rule of thumb is to gravitate towards the benzoic acid, but let's try to understand why, right? What else, does having that, just having an NO2 there do to the ring? Just having the NO2 there still puts a positive in the ring. It still puts a positive in the ring. And so because there's still a positive in the ring, that's not something that's available here, right? There is an overall delta positive here, but there is nothing in this ring. So still, this guy is better. This guy is still way better, way, way better. Okay. Again, because we're taking into account, what have I learned, right? What have I learned about this system and applying it to the broader scope of things? Okay, so don't freak out if you see something that I haven't or you haven't seen discussed in great length. Use what you know that has been discussed in great length to rationalize an answer. That's like the key MO, right? That's like the key part of the series class is, she teaches you all the rules so that when she breaks them, you can appreciate why she's breaking them, right? It's because she's pushing you. She's pushing you, just like how I'm pushing you now. Okay, cool. So that's benzoic acids, and I'm going to just, keep it there. If there's anything more to be said, it can be said later. Okay. But now that we've done that, let's just move on to, the carboxylic acid in general, its preparation and its reactions. Okay. Now, a little bit of a reminder, because it's now been such a long time that we've been here. But remember that we initially talked about how there is this OH site that can, that we've seen react back in 118A, right? And then there is this carbonyl site that we saw react back in 118B. And what we'll realize is that a lot of those things that we saw are going to be pretty much, kind of, or not pretty much, but kind of the same, right? For example, we kind of talked about how if there is the ability for the carboxylic acid to act as a base, or for example, right, if we were to give this H plus, right, we would see the carbonyl act as a base. So there is a basic site on the carb acid. Okay, there is a basic site on the carb acid. And so if you need to remind yourself why the carbonyl is a way better position to do this on rather than the oxygen, right? So if there is an acidic condition, we might expect this to be like our first thing to occur, right? We also briefly talked about how if there is anything basic in solution, okay, and that's why I remind you guys, right, to think about basic things, right? What were those basic things that we gave stars? Maybe go back and look at those again, right? But if there's basic things, right, they're going to grab this proton here. So this is oh, sorry, I labeled this wrong. I think because I saw acidic. Let me put it this way so it's not confused, because I mean, it confused me, so I imagine it confused you guys too. So this is sort of the basic site, okay, which is what we're going to expect in acidic conditions, right? And this here is the acidic site, which we're going to expect to react in basic conditions. It's a little bit of it's a little bit of a vice versa kind of thing, right? And we gave values, right? This is a value of 5. And this here is a value of -5. Okay, so I want you guys to keep this in mind as we move on forward, right? And look at reactions and consider, when we might want to do one of these two things. Okay, but before we get on to that, that was just a little bit of a reminder because it's been such a while since we talked about that, right? Let's get into the preparation of carboxylic acids in general. Now, if we go back all the way to 118A, so if you want, we can even section this off. We can call this 118A, right? Do you guys remember how we made carboxylic acids back in 118A? Such a long time ago too. So don't worry if it's slipping you how to do this. But back in 118A, really the only systems we had was the alkyl halide and the alcohol, right? Of these two things, right? Which one do you think is better to make the carboxylic acid from? Hopefully you remember that alcohols, right? We can oxidize them to the carboxylic acid, okay? But it's not like halides are bad because we can make halides into alcohols, okay? So a little bit of 118A roadmap was alkyl halide to alcohol to carboxylic acid. So let's actually kind of remind ourselves of how we did that. Let's take this ethane here. So you guys remember what we did if we only had ethane, a boring carbon chain? What was the only reaction we can do? It's going to be Br2HV, which brominates a carbon. And we can turn this alkyl halide into an alcohol via SN2. Okay. And again, we can do an oxidation here that takes us all the way to carboxylic acid. Now, this one here was that Jones reagent, right? Which was that chromic acid in the presence of water. Okay, but this is one way that we can make carboxylic acids. Okay, and so really, if you think back to 182 new chemistry, anytime you can make a primary alcohol, so in 182, making a primary alcohol, it gave you access to the carboxylic acid. Okay, give you access to the carboxylic acid. So let's think of other ways we can get access to the primary alcohol, right? We can continue on our journey or continue using this one or this 2-carbon fragment to bromine. But maybe instead of doing an SN2 here, right? Maybe what we do is we turn this into a Grignard. We can also turn this into organolithium. Grignard is not necessarily a requirement. So this could have been Li as well. That's just adding, if you add in lithium metal, it will turn this into just Li here. But we can do Grignard too. And so why is it that I want to do Grignard? It's because, hey, we just have to make primary alcohols, right? If I add in formaldehyde, followed up by aqueous workup, what I'm going to get here is going to be this compound here, which is a primary alcohol. I want you to notice something here. Notice how we add a carbon oxygen, right? So we add a carbon oxygen. Okay, so a little fragment that we've added here that's a little bit different, right, from the first one, because the first one kind of does the same thing where it makes primary alcohol. But notice how 1, 2, 1, 2, 1, 2, 1, 2. We have the same number of carbons. Here we've kind of added carbons, right? We've added carbons. So we've add 1 carbon. So we've actually ended up adding a carbon in this instance, okay? We can also have added something else. We could add an epoxide, okay? We can add an epoxide and do the same sort of workup. And what do we expect here? Sort of the same thing. Okay, but again, what I want you guys to recognize here is that now, instead of having 1 carbon and oxygen, we have 2 carbons and an oxygen. And so it should not surprise you then when we look at this fragment, it's adding 2 carbons. Okay. And then I could do Jones here. And I get a carboxylic acid. Okay, and this adds 2 carbons. Okay, so why might this be important? Well, imagine you're doing a synthesis on the exam and you notice that you've added 2 total carbons to your system, or you added 1 total carbon, or you stayed the same number of carbons. With 118A chemistry, we had ways of doing that, right? Of adding in those particular sort of segments. Okay, now there is sort of another way, I suppose. I just realized you might remember that we could do a PCC here, although I don't know why you'd want to. Really, if anything, you would start from an aldehyde, because if you have a primary alcohol, you just want to go straight there. But if you start from an aldehyde, you can do this. It's just Jones again, but just a little bit of reminder that we can do that. Technically, you could go here to here, but why would you do that? Just add in the water. You're going to add in water the only difference between these two is just water, so you might as well just add it in the first time, right? No point in wasting time on doing that. Okay, so this is sort of the 118A chemistry that we could take advantage of. Okay, 118A chemistry we could take advantage of. 118B, so 118B, there was sort of a couple of, I want to say, oddball reactions, right? So we can actually get rid of those first thing. Those are probably the first ones we want to talk about. The first oddball reaction is the following. It was KMNO4. Okay, and KMNO4 actually in general is kind of a weirdo. KMNO4 kind of just does all the things that are weird in this class. But if we have KMNO4, and I wonder, I guess we could put it in water and heat. I'm pretty sure this is heated. Yeah, so KMNO4 heated, oh, and H2OH plus. Okay, what we're going to get is going to be the following product. Now you'll notice here that what we're forming here are carboxylic acids on 2 of these carbon groups and not 1 of them. And if you remember, the main sort of leading component of this reaction was benzoic hydrogens. As long as there was 1, this reaction would work, right? So we'd see benzoic there, right? Benzoic there. But notice how there are none here, right? And so that's why that reaction didn't work there. And again, like I mentioned, KMNO4 just in general is a very reactive group in, in such a way. KMNO4, if we run this reaction with an alkene, very, very hot. Okay, so really the point here is it's just a normal non-aromatic alkene, and it's very, very hot and heated. We can get that sort of similar cleavage we were used to here, right, with ozonolysis. But in this case, this actually completely oxidizes into the carboxylic acids. Let me actually draw this the other way. But what should have been an aldehyde, right, what should have been an aldehyde ends up becoming just a carboxylic acid. Okay, you can achieve the same thing actually with ozonolysis. Just use a oxidative workup. You might be used to this being here SCH32. That's what gives you a reductive environment, and that's what gives you the ketone and aldehyde. But if you use H2O2, which is an oxidizer, it actually gives you the carboxylic acid in place of the aldehyde. So there should have been an aldehyde here, right? Instead of aldehyde, it's going to be carboxylic acid. Okay, so that's one of the oddball guys from 118B that can do this reaction. One of the coolest reactions actually is going to be this reaction here, which does have benzoic hydrogens. In this case, it has 2, but it could have also had 1. This still would have worked. But we can do the same reaction set here. And what we get is this here. And we'll actually learn in a second what we can do with dicarboxylic acids in a position like this. We can actually manipulate them even further. So this molecule here actually has a lot of synthetic value. Actually, I wanted to keep it a secret, but it's whatever, it's no longer a secret. This molecule here, this dibenzene known as naphthalene, you can actually use KMNO4 to turn it into dibenzoic acid or diorthobenzoic acid. And diorthobenzoic acid, you can do a lot of things with this molecule. Okay, and it's completely cleaved by this here. So I'm going to just put the quotations to say that these are the same conditions. Okay, so really cool reaction there. Okay, 118B also had this other oddball reaction with aldehydes. It had quite a few actually. We had MCPBA, which always turned aldehydes into carboxylic acids. It's sort of like Jones. Sort of like Jones in a way, right? It does exactly the same thing. Highest migratory aptitude is the hydrogen. Okay. We also had those toluenes and phtalanes. You might remember that these guys were oxidative tests for aldehydes. And so aldehydes, if they were present, these tests would be positive. These guys would be positive. Okay. And then there's one last sort of, I don't even really want to call this an oddball. It's not really an oddball because it's really important. But the very last one involves what we call a methyl ketone. Okay, a methyl ketone. So if we have a methyl ketone, we have a methyl ketone. What we can do is introduce it to X2 NaOH, right? And what that would give us is a carboxylate that we could then do acidic workup on. I guess I could have put this all in the same arrow. I just didn't have that space. Right? But we can get a carboxylic acid. And I want you guys to notice here is that if we started with 2 carbons, we're now ending with 1. Or sorry, so we started with 3 carbons total. We're now ending with 1. So we lost carbon here. So this is kind of a corollary to the previous page where we could same number of carbon, add a carbon, right? We can also lose a carbon. We can also lose a carbon. Okay, and this is the way that you would do it. So if you're doing a synthesis and you notice, hey, this is going from, 5 carbons to 4, I'm thinking this reaction here. Okay, and so this is sort of the 118B carboxylic acid transformations. Now, 118C also has carboxylic acid transformations. Okay, and actually one of these we learned in 118B. I'm just including it here because it makes more sense to include it here. But you might remember we talked about nitriles. So what are nitriles? You might remember we can add to a ketone NaCN, HCl. And so that would give us CN here and OH here. And this one you might remember, maybe you don't, but if I did H plus H2O or I did OH minus H2O into H plus H2O, so step 2 is just this here, what I would get is a carboxylic acid in place of the nitrile. Okay, so essentially nitriles are masked carboxylic acids. And so there was 2 systems that we kind of used to add NaCN. We also added NaCN here as well. And if you need help remembering, this does the 1,4 addition primarily. Okay, so it adds on this carbon here. Okay, and so what we get is a nitrile. And again, if we do that same hydrolysis, so I'm just going to put hydrolysis here. These conditions here are hydrolysis, whether you do H plus H2O or OH minus H2O, doesn't matter. But if I do hydrolysis, I get the same thing, that same result, that this becomes an acid. Okay. Hello. There we go. Sorry about that. Mike's just in the go out today. But yeah, anywhere we can install a nitrile means that we can essentially install a carboxylic acid. So this actually kind of, brings a new light to the reactions we were doing before. So here, let's do a little test here. I'm going to draw intermediates, and you guys fill in the blanks. Right, but we have the availability of this mechanism here. These are the blanks here. Remember, HCl is for carbonyls or for enones. You would use DMSO if it's an alkyl halide. But I can just do H plus H2O here, and what I get is a carboxylic acid. Okay, this also adds 1 carbon. See, that adds 1 carbon, right? That adds 1 carbon. Okay, so again, anywhere we can install this nitrile, that's essentially saying we can install a carboxylic acid. That's great. That's great. So basically the SN2 we did in 118A is now a little bit enhanced because we can use H2SO, sorry, we can use nitrile here instead, right? Also a pretty cool thing is actually going to be another sort of augmentation of a 118A reaction. We can also do the same thing. And again, you can fill in the blanks. But if I add a Grignard, right? Remember, if I add a carbonyl, right? So if I add a carbonyl, the carbonyl reduces into CO, right? So this reduces into COH like that. So all I have to do is be clever with what kind of carbonyl I add that reduces one carbonyl but keeps the other. Basically, this is just my convoluted way of saying, if you use CO2, which is 2 carbonyls in 1 carbon, right? So CO2 into H plus H2O. Instead of getting just OH here, right? Which you would get if I use formaldehyde. One of these carbonyls is going to be unaffected, right? And that carbonyl is going to stick around. And this is another way to add one carbon to a carboxylic acid synthesis. Okay, so two very valid pathways to add one carbon, and you can kind of see from this that there might be a little rivalry here, because truly, right, if both things do the same thing, right, maybe one is better, maybe one is worse, right, or maybe it doesn't really matter. Well, when it comes to these guys down here, so this is what we need to learn specifically, or we need to understand now for 118C, right? When do I want to use what I call the nitrile synth? Let me not use this color, actually. I don't want to give the false impression, but when do I want to use a nitrile synth? And when do I want to use the Grignard synth? Okay, there's sort of three things I would look out for to kind of figure this out. Okay, the first thing I would look at is substitution. So what do I mean by that? Well, remember that this reaction here is an SN2 reaction. Okay, this is an SN2 reaction. This reaction here to here is what we call a metallation. Okay, the reason why we need to look at substitution is because remember, SN2 is really good on primary. It's okay on secondary. It's amazing on methyl substrates. But when we get to tertiary, this reaction really, really sucks. Okay, so nitrile synth is a little limited if we're using anything that's not methyl primary. Even secondary, I would say, is pushing it, right? But tertiary is just not really going to work for the nitrile synth. Okay, that's just not really going to work. Actually, let me put it this way. So for nitrile synth, tertiary is not going to work. Maybe I should do it with this color. So methyl primary, secondary, tertiary, these will work. Okay. On the other hand, when it comes to Grignard, Grignard as a metallation, metallations don't have substitution issues. They can work on any substitution. Okay, so maybe this is a point in the Grignard bank. Maybe this is what we want to use. If you can't figure it out from there, what then I would look at is hybridization. So let's imagine they're both primary, right? And you're like, okay, it's primary. I don't know what to do. Then what I would look at is hybridization. Let me actually make this smaller. Okay, so what do I mean by hybridization? Well, again, as an SN2, right, and again as a metallation, SN2 reactions, again, are only going to work on sp3 centers. Okay, so there's sp3, sp2, sp, right? And again, only going to work on sp3 centers. They do not work on sp2 and they do not work on sp. Okay, not going to work whatsoever. The other hand, right, if I have a metallation reaction, metals don't care what the substitution is. Okay, or sorry, what the hybridization is. They'll work on any of these. And so this might be another token in the Grignard bank, right? And you might be thinking at this point that, oh my God, Grignard looks so good. Like, why would I ever use nitrile? There is one instance where nitrile will be better. And that one instance is going to be basicity. And when I say this, I mean the presence of NH, OH, and SH. We know that nitriles are not basic. Okay, so that's great. But Grignards are very basic. And so if there is ever the presence of a acidic proton, OH, NH, or SH, Grignard is just going to fail. So to kind of prime you to these ideas, I'm just going to draw 3 examples here. Right, and take a second to think about, right, which one, if not both, right, reaction works best for either system. Okay, so pause and think about that for a second. And so hopefully you pause and thought about that. And again, to tackle this, again, just think, right? Substitution, right? What is this carbon? It's primary, so both work. Hybridization is sp3, so they both work. And there's no basic indication of any basic group. So both of these will work great on this one. On this one, right, substitution, primary, so both work. But hybridization, this is sp2. And therefore, Grignard is the only thing that's going to work here. So I would want to use a Grignard synth here. Okay, finally, right, what do I see here? I see a primary, so both work, sp3, both work, but there is a presence of an OH. Therefore, I would never, ever, ever want to use Grignard. I'm using nitrile. Okay. So that's kind of the idea when it comes to using one over the other. And this is one of the most common questions on an exam this series will ask, because she wants to see if you're thinking, right? I guess if I wanted to give one for, so I gave one for hybridization and basicity, substrate would be like, if I had this, I think this was a problem once. Like if I wanted to make this acid from this starting material, right? You can actually do the map for this. So if I started from here, right, what's the only thing I can do is bromination, so it goes there. I would use Grignard here because SN2 sucks on tertiary, so MgBr. And then I would do CO2, right, which would give me this. Now, here is a good one. What if instead the answer was this? So CO2 is the answer. So if it's this, it's CO2, right? But what if it was actually this? Ooh, that's a hard one, right? Because you have to think really hard here, right? How many carbons am I adding? I'm going from 6, right, to 6, 7, 8. So I'm not going from 6 to 7, I'm going from 6 to 8. So I added 2 carbons. So what's the method back here that adds 2 carbons? It's going to be an epoxide. So although the first one we showed was CO2, this is going to be epoxide into Jones. So don't just think that Grignard only does one thing. Grignard could add 2 things, right? Grignard could potentially add 2 things to make acids. So be on the lookout. Always be on the lookout for that. Okay, cool. So those are the different preparations of an acid that you might want to keep in mind. Now, a little bit of like reminder, or not a reminder, but advice. In my opinion, when it comes to 118C synth, which we'll go over way more in depth for, we'll do a lot of practice problems for the synth guide. It's really, in my opinion, the formation of the carboxylic acid that's the hardest part, because forming a derivative or forming something from a carboxylic acid is really easy. So turning this into any part of the carboxylic acid family, which we're going to see upcoming, is not a very hard thing to do as long as you know what to do. As long as you recognize the functional group, really. Like if you're going to, let's say, like an ester, that's really, really easy actually from here to here. Going from amide, really, really easy. Going to acyl halide, even easier, right? That's not the hard part. The hard part is figuring out how do I even get to the acid in the first place and do those transformations. Is what we're going. Hello, hello, hello. Sorry about that. Cool. All right. So let's get into the first reactions, right, of the carboxylic acid with its family, right, with its family. And so I guess maybe it might be good to just introduce the family now. So the carboxylic acid is part of a whole group of other carbonyl compounds. Okay. And what these groups have in common, you might notice is, well, yeah, they have a carbonyl. That is one thing they all have in common. They all have a carbonyl. Okay, but what makes them very interesting is that on top of having a carbonyl, which is something that a ketone and an aldehyde also had, they also have what we call an X group or a Y group. You might have heard either term, but they have a group adjacent to the carbonyl that is a lot different from the H and the methyl that we're used to seeing in the ketone and the aldehyde. And so having these groups here can really change the reactivity of the system, and they can really change how we view certain reactions to occur. Okay, namely, the biggest thing is that, remember with ketones and aldehydes, like if I reacted a nucleophile with this ketone, what we noticed was that we would always get an intermediate like this, and this intermediate was relatively stable. Stable meaning that nothing could really happen at this point. Carbonyl could not react any further. It would typically just, have to wait around till it gets protonated, right? And what we would get is either a alcohol nucleophile product, or this would be some intermediate to some further product, right? So this would either stop here or it would continue to go further. The cyanohydride is actually a great example on the back page, right? Cyanohydride just adds on, and that's just our end product, right? And really the reason why this was stable is because there was nothing on the the oxide here that could really do anything like leave. One thing that you kind of haven't learned yet, but I guess it's good to mention, is that carbonyls are very favorable structures. When you take biochem, you'll really understand why that is, especially in the human body. But carbonyls are so favorable that if they can form, they will form again. That's a big reason why a lot of these nucleophile additions were reversible. It's because sometimes the carbonyl is just better than whatever adduct we're adding to it. So if this could come down again, it would, and sometimes it would result in the nucleophile leaving. Now, if we didn't want the nucleophile to leave, we would need some kind of leaving group. And that leaving group would have to be one of the two groups on the original aldehyde or ketone. Now, the reason why it turns an aldehyde is kind of illustrate 2 points, or kind of the same point with two different things. If either R or H were to leave, that would be an R minus or an H minus leaving group. So these blue guys here would be leaving groups H minus or R minus. These guys are crazy basic, like the most basic things ever. And basic things don't want to form, right? They don't want to form at all. They want to stay, put where they are. And so that was the reason why we would call the ketone aldehyde intermediate stable. It's because they don't really want to, kick off a new group and leave. Well, with the introduction of this new X group that we'll call, right? It could be let's use Y because I don't want you to confuse X with halogens, right? Now, when a nucleophile adds on, whether it's reversible or not, we will get to that, right? But let's just say irreversible for now, right? Well, here's the thing is that when the carbonyl comes down, there is a potential for the nucleophile to fly off and this goes backwards, but now we have an X group that's a little more acceptable as a leaving group, and potentially we can get a new carbonyl compound. So if this here is simply an addition of a nucleophile, right, because nothing really leaves here, this here would be a substitution, okay, because something is leaving, the X is leaving. And so the acidity of X or the leaving group ability of X is really what's going to help, push these reactions towards substitution as opposed to addition. So we're going to see in a couple of these reactions that, especially the carboxylic acid reactions, OH is going to function as a leaving group. Okay, and we're going to reform our carbonyls. I mean, like I said, right, these guys are all a family, and we're going to see the reactions of the carboxylic acid becoming all of these guys. And so it's contingent that OH acts as a leaving group in order for this to be the case. Okay, so a little bit of a difference that we should come to expect for these reactions. Okay, but it's a welcome difference. Okay, makes our lives a little more interesting. All right, so the very first reaction, okay, the very first reaction we're going to look at is the carboxylic acid transforming into that acyl halide. Okay, and so again, as I've always been doing, let's try to understand this reaction on a level we've already seen it before. If we think about what's going on, the OH is turning into a Cl. Well, wait a minute. We've seen that before. We've seen OH turn into Cl before, right? How did we do this reaction in the past? One way we did it, let's actually use, for this one, let's use bromide because halogen bromides are just a little bit better. Actually, no, whatever. Let's just keep it chlorine. It's okay. But in the past, one way that we saw this reaction was with HCl, right? Because this would just become protonated, and then Cl minus would just do an SN2 attack, right, and kick it off. So maybe what we can do is we can add in HCl. Okay. So what would happen here? Well, remember, HCl is acid. And what did we say right before we started the reaction segment? What was that reminder? That this is the acidic site that reacts in basic conditions. This here is the basic site that reacts in acidic conditions, right? Where do we put it? Put it back here, right? The basic and acidic site. Who takes the proton? It's going to be the carbonyl oxygen. Okay. And so the carbonyl oxygen can react here. And in the past, when the carbonyl oxygen reacted to make this system here, right? Why did it react to do that? Or what has as a result? The carbonyl becomes more electrophilic. And so as a result, if there's any nucleophile, basic or non-basic, right, it might attack here. I guess I shouldn't say basic or non-basic. I should say basic or nucleophilic. This is more nucleophilic than basic, but Cl minus could attack there. And so what results is this system here. Now, currently, there really is no good, currently you might think that this OH is not a good leaving group. So maybe what you might want to do is protonate this, and we'll do it just for the sake of argument here. We'll say that this OH picks up a proton. But when these electrons come down to reform the carbonyl, right, who is going to leave? Think about this really hard. Who is going to leave? I think a lot of you want to kick off the OH group here, the OH2 plus group, because that's what makes sense. It's what feels familiar. And then you get the acyl halide like we want to. But water, although being a good leaving group, it has a pKa of -1. Cl has a pKa of -5. So who is more acidic, right? Who is more acidic by pKa value? Lower the number, the more acidic. So Cl is clearly more acidic. So if acidity, higher acidity means higher leaving group ability, right? Again, concept for 118A. Who is going to leave? Well, if chlorine is the more acidic, then chlorine is going to leave. And now suddenly we've accidentally just gone backwards. Even if we protonate this, right, we still don't force it to leave. And in actuality, this will actually come down and kick off Cl immediately. We won't even go through this pathway because that's how good of a leaving group Cl is. It's going to jump off. So HCl is not going to be a good reagent, a good material for us to make acyl halides. And we can see why. It doesn't turn oxygen into a good enough leaving group, right, to become the acyl chloride. So we have to use something else. Can't be HCl, has to be something else, okay? And what was the other thing that we used in 118A to make alcohols? It's not HCl, and it's SOCl2. And so how did SOCl2 work, right? If we want to remind ourselves with a rough mechanism, right? It worked by the alcohol attacking SOCl2. And what resulted is this here. So remember, the carbonyl acts as an electron sink, which is why the electrons go up there. This comes down and kicks off one of the chlorines. And then one of the chlorines, right, just kind of displaces out oxygen, right? And that's how we get the acyl chloride. So let's see how this might be applied if we use this mechanism, right? This mechanism to turn carboxylic acids into, oops. Oh man, it's been so long I've been doing this and I still can't get it right. There we go. So let's see what SOCl2 can do to a carboxylic acid if I use it. Okay, so SOCl2. Well, again, right, alcohol lone pair kind of attacks this sulfur here. And so instead of getting this oxygen here like that, what we'll get is this here. Sorry, we won't have a proton on that oxygen. What we're going to have is a SOCl2. So far, everything's just kind of the same as we've done it before. Okay, and so now we've gotten to this point here. And what happens, right? Cl minus again attacks that carbonyl center. That's now a little more electrophilic. And what we get is this here. Okay, so the chlorine's in place now. Now all we really need and I'm drawing it this way on purpose. Don't worry. There's a reason why I'm doing it this way. Oh, sorry, I wrote you the wrong thing here. Yeah, sorry, this can be here again. Okay. Again, what do we need to get this reaction to work? Well, we need for this group to leave, right? Because if chlorine leaves, then the reaction is going to be over. So what do we need? We need when this oxygen comes down here, we kick off this group and we don't click off chlorine. Turns out exactly what we want happens. What happens is this is going to come down and we're going to kick off this oxygen group here. Okay. Now we could draw it this way if we'd like, right? To show that this whole group here is going to leave. That's totally possible if you want to. I like a different mechanism because I like cyclic mechanisms. If you guys, remember, this one's actually a really cool one. This chlorine can actually grab this proton here with its bond. This bond between O and H come to form a carbonyl here. And then the bond between carbon and oxygen here is going to break to make a double bond there. What this results in essentially is this. The three components that we would expect of the reaction. So do whatever you want. I just think this one looks really cool. So I like to instead of the Cl, and we're able to nicely isolate out SO2, or sorry, nicely isolate out the acyl halide just like we want. So that's really, really great. Makes us really, really happy. Now, one thing you might want to notice here is that we form HCl, and that's a very bad thing because HCl is toxic. It will kill you. Okay, so in the lab, I'm actually going to use SOCl2 soon. I'm actually not allowed to use it on my own because of this issue that it could be toxic, right? That it could hurt me potentially. But a way to kind of prevent, the formation or the accumulation really of HCl, what you can do is you can add in some kind of base. You guys are going to get very, very familiar with this base. We can add in pyridine. And so the mechanism is going to be slightly different with pyridine than it is going to be with SOCl2 just alone. So I'm going to go ahead and I'm going to erase this. But remember back when, right? Remember how we talked about how the carboxylic acid has like more acidity in general and even amines can react? Well, not only can sp3 amines pull off the proton, but so can sp2 amines. So pyridine's an sp2 amine, and it has a pretty good basicity compared to a carboxylic acid. Essentially, what you need to know is that even sp2 amines will pull off the proton off of a carboxylic acid, and what we form is the carboxylate. Now, you might remember this from 118A. The carboxylate sometimes can act as a good nucleophile, okay? And so the way we're going to use it, just like how we did the, oh, I realized I should have mentioned this. So I did the attack, the basic attack that we did here. But remember that this is the resonating system, right? So we can also do the attack a different way too. And actually, I prefer doing it this way. I just realized doing it because I drew that arrow in there, but I prefer doing it this way, where we drop the electrons like that. Because again, it shows your reader that you know that this is resonating, right? And really the electrons are going to flow through and then attack. Kind of the same thing here, right? Electrons are going to flow through and then they attack. Okay. But we're going to have a similar mechanism to what we've seen before. Okay. Oh, sorry, there should be a minus here now. Okay. And again, sort of the same things we've seen before. I'm going to draw this right side up, or actually maybe I can keep it this way. If I remember correctly, we can't do the cool thing. Yeah, we can't do what I want to do here, but chlorine can go ahead and attack here. And so, no matter how I try, I've been trying to think actually in this past couple seconds, can I still do my cool cyclic mechanism? I don't think that I can. I don't think that I can, unfortunately. But we can go ahead and drop this and then kick this guy off. We can do something like that. It's just not cyclic like I like it. End result of this, right, is just going to form that acyl chloride, SO2, and HCl. I know I drew these guys sideways, but sideways doesn't matter. We can flip it over. It's going to turn into this. Okay. Oh, sorry, not HCl. What am I doing? That's the whole thing we were trying to avoid. It's going to be SO2 and Cl minus that is coordinated. Not really not coordinated, but it's going to be salted to the pyridine that earlier took a proton. Okay, so that's how we perform, or that's how we avoid the formation of toxic HCl gas. Cool. So this is how we make acyl halides. And again, we use chemistry we knew. So even if we weren't sure, we can use chemistry from the past and really give us a good idea how to guess. Now that classes are online and we have to do in-person exams, you might be a little afraid that you might forget to help us predict what we need to do. Okay, it's that way we can succeed in this class. So there you have it. That's how we make acyl halides. The next person in the family is going to be carboxylic anhydrides, or acid anhydrides, or acyl anhydrides, whatever you want to call them. Even anhydride by itself is okay. And the name is interesting because the name says anhydride without hydration, right? Without water. And so you might be wondering, how does that name fit in? Well, if I took 2 carboxylic acids, okay, and I were to heat them, taking out these 3 components, or these 2 components here that equal water, right, would give me this and this. And you can see that if I just added this piece to here like that, right, what would that give me? That would give me the anhydride. That would give me the anhydride. Okay, so we can actually dehydrate carboxylic acids, right? And that will give us anhydrides. Now, this process here is an industrial process, right? Like, it's not a very synthetic process. This is if like you had a huge vat full of carboxylic acid. You could, put it under a burner. Let this heat for a very long time, very, very, very long time, right? And over days, months, years, centuries, whatnot, you would, make these anhydrides. But again, that's industrial. That's like if someone doesn't really care about the time frame in which they make this. As a synthetic organic chemist, just even from me, someone who does this for, just participates in the lab and does this stuff, I would never want to wait a day for a material. I want to lessen that to hours, right? I want a process that I can do within one workday. I don't have to wait a day if I have to. Okay, waiting days is an industrial process. This is like on the business scale of things. I'm on the synthetic scale. I want things done immediately. I'm an impatient person. So this is not the greatest synthetic, utility here. But there is a good industrial advantage to this, because it's like one component you have to heat and you get this. And also, right, one thing that also kind of sucks is that there is no like sort of scrutiny on what carbonyl compound attacks which one. So you might actually remember this from 118b if you remember Claisen condensations. Remember how Claisens, aldols is what I meant to say. Remember how with aldol condensations, if I use 2 different carbonyl compounds, I'd get a lot of products. Same thing here. We don't know if this guy will dimerize or this guy will dimerize. We also don't know if they will dimer, make an asymmetric dimer as well. So again, really, really bad process to do with mixes. Um, even worse than the previous one. I would rather do this than do this any day. I would hate to have to, these are all the same. How would you separate them? I wouldn't know how to do that. I would struggle for days figuring out how to separate these compounds here. So you really, really, really don't want to be doing this here, okay? But that doesn't mean that it can't work, right? Some molecules are better suited, for example, like intramolecular molecules. So you guys actually might recognize this. This here, if I were to heat it, would give me this molecule that you guys are all probably familiar with. This is maleic anhydride. Okay, this here is maleic acid. Okay, and maleic anhydride, maleic acid, you can heat these guys up, or maleic acid, you heat this guy up, and you'll get the product that you want. Okay, again, really just up to the time scale that you're willing to accept on this kind of reaction. Now, you don't necessarily need the double bond there. You might think that you need it. You don't actually really need it. You can even just use the aliphatic, non-double bonded. I guess they're both aliphatic. I shouldn't have said that, but you can use just the normal bonded, single bonded variant as well, right? You can imagine there's two of these guys, right? There is the 5-membered variant, which would be, how many carbons would this be? 1, 2, 3, so 2, 3, 4. So this guy can be heated to make the 5-membered variant. You can imagine even the 6-membered one, like you could make a 6-membered one from this too. Just look a little odd. Right, this would just be if it's instead of 4, it's 5. Okay. Now, there is a better synthetic way to do this. Okay. And it, this is you're going to see this done a lot, actually. Every single derivative will do this, or every single reaction page, we're going to do this just because it's just so much better. But we can actually turn the carboxylic acid into a better group. I mean, think about it. What's the only other reaction you learned, right? We can turn it into that acyl halide from earlier. And then we can do reactions from here. And these reactions tend to be better. So actually, if I have that carboxylic acid here, this reaction is faster. Okay. If I add in that different carboxylic acid, now I can ensure that I get only the dimer that I want, right? Which was this one here, the mixed dimer. I could use, even on this one here, right? If I did SOCl2, this one is probably, this was actually probably way better. Same as these guys too, right? If I just did SOCl2, probably loads better. Okay. And the reason for that is because, as we'll see in chapter 20, acyl halides are the most electrophilic acyl derivative, meaning that almost anything will attack it. Like even the weakest of nucleophiles will attack an acyl halide. And so for that reason alone, this reaction is just way better to do. Okay. SOCl2 just way better, way better. Okay. Cool. So this is how we make anhydrides. And this thing here, we're going to see for the rest of them. We're going to see how using this SOCl2, right, more reactive derivative is going to help us out. Cool. So now that we see that, let's go ahead and look at carboxylic acids to esters. So OH to OR. Now this one, again, you might just think back to how in the past have I made OH into OR. So let's say OH into this. And maybe one thing you might remember is Williamson ether synthesis. So how does Williamson ether work, right? Williamson ether works by deprotonation, right, of the alcohol. And then what we do is, introduce some kind of alkyl halide. right? So we can get an SN2 reaction. And that is one thing that works. Because if you remember, carboxylates can be deprotonated. Even with pyridine, it can deprotonate. Right? We can really use pretty much use anything. Anything that can take off this proton. Right? And if I add an acyl halide, this reaction will work. And this is interesting because this is the first reaction where we see the carboxylic acid being used as a nucleophile as opposed to an electrophile. Okay, so nucleophile instead of electrophile. And we see that it works. Okay, so that can work very well. So this is an acceptable process. Another way you might remember is that if we add an H2SO4 at a low temp, okay, so I think a low temp, 0C might be a good one. The alcohol can get protonated, and another similar alcohol can come and attack and give us our product, right? Sure, it'll be protonated first, but we can get rid of that proton really easily, right? And so let's again try to apply this problem to the carboxylic acid. So we have H plus. Again, who is going to take that proton? It's going to be this guy here. And once we've made this electrophilic, let's use that same alcohol, this one here. This can go ahead and attack here. Now, similar to the acyl halide, sorry about that. Similar to the acyl halide, you might be thinking, I'm just making more space by getting rid of that one. You might be thinking about how, we had this state here where we could have protonated. So let's actually transfer the proton over, right? Let's do a proton transfer. Definitely draw this out on your exam. Do not just write what I'm writing. But we can go ahead and transfer over a proton just like that. And, when these electrons come down, again, the best leaving group now, right? Before there was a chlorine here, now there's an O minus. So Cl minus versus O minus. O minus is terrible leaving group. OH2 plus always wins here. And so we can actually easily make our ester, right? Again, another proton transfer. That water molecule actually will probably pick this up, the one that just left, right? And what we get is the ester, okay? And this process works very well too. This process actually has a name to it. The name is Fischer esterification, okay? And Fischer esterification is a really great process. Now, this Fischer esterification is a more traditional reaction. And what I mean by that is, like, again, we're using the carbonyl of the carboxylic acid as an electrophile, like we did with the last two reactions, right? Although this one, uses as a nucleophile more so. And one thing you might be wondering, right, is, well, before, right, we added in, a group that made like this group better, right? So with the SOCO2, it made this whole group better than the Cl, right? How much better is alcohol from the alcohol? Or sorry, how much better is the OH from the alcohol, the OR is the leaving group, right? Like, what if here this came down and kicked this guy off? Well, it turns out that this reaction is actually in a really tight equilibrium. So really, we should have used reversibility arrows here. This reaction, if we were to measure how equal, or not how equal, but how favored to the products or the reactants this reaction is, this reaction, that measure is known as Q equilibrium. You might remember that from Gen Chem. It has a Q equilibrium of 1, meaning that the reactants and products are actually very favored, or equal in favorability. Normally, if it's higher than 1, it means the products is better. Lower than 1 means the reactants is better. But in this case, it's 1, meaning that both are about equal. So when we do this reaction, we can do a couple things that can really help us, really help us push the reaction towards the right. Because if we just do the reaction as is, the reaction is going to get stuck at a 50-50. You're going to get a really terrible yield, maybe like 40-50% of your ester, when you really want like 80-90%. So what are some things we can do? Well, if we think about the components, we have alcohol and acid, or we have ester and water, okay? Because water has to leave, right? Water left here, or alcohol gets consumed, right? Two things we can do. One thing we can do is we can increase the amount of alcohol, because if we stress the left side with alcohol, we're going to increase reaction towards the right to consume that alcohol. And so typically what we do for Fischer esterifications is not, even though this is 1-to-1, right? It's 1-to-1 on the mechanism too. We actually do a 1-to-3 ratio. 3 equivalents is pretty much standard required, laboratory standard. You need to use 3 equivalents. That is, if you want to have like a 80% yield, you need about 3. Another thing you can do is you can use something called a Dean-Stark trap. And what that does is it removes water as the reaction goes on. And so if we're stressing the right side by removing water, how do we respond? We respond by making more water. How do we make more water? We push the reaction towards the right. So 2 sort of solutions to this issue. And it might help explain to you why you practically drowned your alcohol in lab, or sorry, you practically drowned your acid in lab with that alcohol. It's because if you didn't, you weren't going to make anything. Like you were destined to fail if you didn't do that. Okay, so it's kind of like a mandatory requirement. Cool. One other thing, just like how we can have intramolecular reactions here, we can also do the same thing here as well. So, intermoleculars are making a comeback. 1, 2, 3, 4, 5. Anytime you see that nucleophilic arm, remember that nucleophilic arm is screaming at you, hey, this is an intramolecular reaction. And so if I just add H+ in both of these cases, right, I'm either going to end up with the 6, or the top one will actually be the 5-membered. So let me draw this 5-membered first. Okay, so 1, 2, 3, 4, 5, or 6-membered, right? 6-membered and 5-membered. Both of these acid catalyzed. Okay. And I would prefer to always use the acid reaction for both of these, and you'll see why in a second. Okay. So intermoleculars are still totally possible. Now, we've done the reaction where we turned the carboxylic acid into the nucleophile and done the reaction. We've also done it in acidic. So a very good question that could come up at this point is, what if we did this in basic media? So basic media would still use the same alcohol, but we would use RO- instead of H+. And remember, back when we talked about what happens with basic nucleophiles, right? What happens if I add a basic nucleophile, right? What's going to happen if I add a basic nucleophile, a basic condition? What we're going to get is this reaction down here. Okay, so let's consider it. So we get a basic reaction, and what we form is the carboxylate. Now, as a nucleophile, as we've seen, carboxylate works as a nucleophile, right? It's a weak one. It's a moderate one, I would say, but it can still work as a nucleophile in this esterification process. As an electrophile, meaning as in, so this takes the proton first. For this to come and attack the carbonyl, that's practically impossible. The carboxylate anion is so stable. There is like 2 or 3 nucleophiles, only one of them you actually even learn in this class, that can destroy the carboxylate. If you ever form the carboxylate, you can pretty much assume it's sticking there for good. Okay, there's really only like 1 or 2 things that can destroy it. Okay, and we'll see that at the end, what can destroy it. Okay, but anytime you form it, any basic nucleophile used to form, and it forms this, just stop there. It's probably going to stop there. Okay, I'll give you a little bit of a hint here in case you can't make it through the whole video, but lithium aluminum hydride is really one of the only nucleophiles that can destroy a carboxylate anion, but nothing else really. Everything else kind of just like lets it hang out. So you cannot do a basic Fischer esterification. You can only do an acidic one. So don't even try it. Okay, don't even try it. Cool. And then one last thing, right? I guess we should talk about this. how do you know when to use, right? When to use the Fischer esterification, the acid process, or to use this SN2 process? The answer really is, it kind of really depends, right? In most cases, it won't really matter, but sometimes it might. For example, let's say I have like a sulfur arm down here, right? And I tried to do let's turn this into a carboxylate, right? And I try to do the SN2 process. Between the carboxylate and the sulfur, sulfur is the way stronger nucleophile. Okay, this guy is the weaker nucleophile. So if I try to do a reaction like this, it really wouldn't work. So the point here being that if there's a competing nucleophile, doing the SN2 pathway is not a very good pathway, because you'll end up getting a sulfur alkylation here. Amines can do it too, right? Amines will also beat. So this could have been a nitrogen as well. But you won't do amine reactions until midterm 2, I think. I'm not sure if she changed that or not, but whenever you do amine reactions, you'll talk about why doing SN2s with amines aren't really good. But this is something to think about, right? Like that is a nucleophilic arm that could potentially impede the reaction, right? Could potentially impede the reaction and stop it from going through. Okay. Another thing is maybe there is something susceptible to acid in your reaction that might make the SN2 better. This one's a little bit of a hard one to think about. So I'm not sure how it would, to be honest, I'm not sure how this would manifest. Something that's, susceptible to acid. But, oh, you know what? Here's a good example. So let's say you had to make this ester here, right? You had to make this ester here. If you do the H+ route, right, and you put in ethyl alcohol, because that's the part there, you will not get this product. What you're going to get is the cyclization product. So really what this is going to give you is this here, because the second this gets protonated, it's not going to wait for the ethyl alcohol. The alcohol arm is going to attack. So really the only way to get this product here is going to be to first deprotonate. So use something mild. Even actually pyridine is going to be perfect here, actually, because pyridine will only deprotonate carboxylic acids. It will not deprotonate here. So it will attack here. It will attack here, but it will not attack here. So you don't have to worry about O- forming. And that will always give us the O- on the carboxylic acid. And that, we can then attack with Br, right? Because, primary alcohols are terrible nucleophiles compared to carboxylate anions. Okay, neutral nucleophiles or a neutral alcohol nucleophile is not as good as a carboxylate anion, and you will get the product you want. So that's kind of what you want to be thinking about if you ever had to choose between the two. If you ever choose between the two, is there possibly some competing reaction, right? Some competing reaction that might make one process better than the other. It's kind of like how we did that, what we did for back here, right? Kind of the same thing. Cool. So that is the ester reactions and what to look out for on them. All that really leaves us now with is going to be the amides. And this is what I would call the end of the traditional, carboxylic acid family. And hopefully you'll see what I mean by that in a second. Okay. But how can we make these guys? Well, again, if we think about OH to NH2, we really can't think about that because we've never done it. Right? You've never learned how to make amines from alcohols. So unfortunately, we don't have a sort of correlating reaction to this. But if we kind of use the same logic that we've been using this whole day, right? What we might have noticed is if I just add an H+ and the nucleophile, the hope is that, or some kind of like activating unit, like some kind of Lewis acid that can activate the carbonyl. The hope is that the carbonyl gets protonated and then the nucleophile can attack. So the hope here is that this will happen, right? This will protonate and then the amine here will attack, right? And that's great thinking if that's what you thought of, right? If this to you makes sense, that's great because it means you've been paying attention. But here's the thing. Remember what we said earlier? We said kind of two things. One thing we said was that amines will deprotonate carboxylic acids. Okay, so one thing is that amines will deprotonate carboxylic acids. The other thing is that if an amine can deprotonate carboxylic acids, that also means that, so really the two things here are kind of the same. Either the amine does this or it does this, right? And so you can actually avoid doing this by just saying, hey, just take out the acid, right? Amines are nucleophilic enough anyways. Well, it doesn't matter because the amine is just going to do that. And what we're going to get is a carboxylic, or really an ammonium salt, a carboxylic ammonium salt. Ammonium carboxylate is probably what we want to call it. Ammonium carboxylate. And just like the CO minus, like the carboxylate anion, this salt is so strong. It is incredibly strong. And really, anytime an amine is in front of a carboxylic acid, this is like the first thing that's going to happen. Okay, it's like the very first thing that's going to happen. And so this causes a little bit of issue because then the question becomes like, what are we going to do? Like, how are we going to deal with this? You could heat this, but heating this takes a really long time to reverse back to here. And eventually you will get the nucleophilic, acyl substitution. So if it's substitution, OH is going to become NH3 or NH2 here, right? You will eventually get to this point here, but by golly, it's so hard to do that. This is another example of something that takes a very, very long time. Industrially, it makes sense to do reactions like this because the yield is still pretty good. The yield is like 90% if you just heat it for a very, very long time. But synthetic chemists don't have that time. We don't have 3 days to wait on our amides. We need our amides now, right? So no synthetic chemist is going to think that this is a good idea unless they absolutely have to, okay? Unless they absolutely have to. There's no other way around it, then we'll just suck it up and do it, right? But there are other processes we can do to couple these two things together. It's not only just heat, but this process, do not ever do it in synthesis. Oh, this just reminds me, I forgot to do something in the last page too. Do not do this in synthesis. Nasiri will dock you. Okay, I think she even tells you in lecture, do not do this. It is a terrible process, terrible, garbage process. Okay, what's better is what I mentioned way before when we were talking about how to make anhydrides. What did we turn this into? We turned this into an acyl halide, a more reactive, the most reactive derivative. And then that acyl halide reacts with excess amine. Okay, so this here, XS, it just means excess. That's just shorthand for it, in case you aren't familiar with that. And that forms amides. Okay, that's how we form our amides. All right, and the mechanism here is not too crazy or anything. I know I didn't show this one, is because, there's, you don't really need to know that because you're never going to really do that. Really, what you might want to, do is this one here, but this one can actually proceed neutrally to make the O minus, NH3 plus, and Cl. O minus will come down and kick off Cl practically immediately because Cl is such a good leaving group. And what we get is NH3 plus. Something in solution will pick up that proton there. It's either going to be NH3 or it's going to be Cl minus. But remember, this is a pK of 9, pKa of -5. Who is more basic and who is more acidic? The more basic compound is going to be the higher number. It's going to be NH3, so another NH3 is going to pick that up. And what we'll get is this here, and then we'll get NH4 plus Cl minus, so ammonium chloride. Ammonium chloride is actually pretty useful. It's a pretty useful workup molecule, or workup solution, is what I should say. Okay, so that actually reminds me back here, there is one more way we can make esters. we can make them through acyl halides. That's another thing we could use if we had to. Okay, and that also is another solution to this problem here, is that we could also just turn this into an acyl halide. Well, actually, no, you can't. No, you can't. Because what do you guys think would happen if I turn this into an acyl halide? So try to answer that on your own. What do you think would happen if this turns into an acyl halide? What would happen? If in the same way this alcohol can attack this acyl halide to become ROH here, what do you guys think would happen in this case? It would attack itself. The second it forms, it would attack itself. It's the same issue with using H+. So this truly, the only way to do this one is to do it the way with deprotonation into ester attack, or sorry, carboxylate attack, right, of this guy here. So truly, this is like really the only way to do this one. Cool. So again, amides, right? Very terrible to make just from amines and carboxylic acid. So do not do it in synth, although industry is fine. Do the acyl halide way. That's the way that Nassiri accepts it. Okay. Very last thing on this is just like we talked about before. The intramolecular reactions also work here. I guess you could do heat here if you wanted to. I'm not sure if heat makes a difference with intermoleculars, but I would always just do SOCl2 because it's the same thing that we saw with the previous page, right? SOCl2 turns this into a Cl, and then NH2 makes it cyclic. Okay, this is just going to attack right there. You could imagine that this here would just eventually make the 6-membered variant. Okay, cool. And that's all we're going to say for now on the amide. So that just kind of leaves us with 2 more reactions that we need to get comfortable with. And the first one is going to be reductions. Okay, reductions. And this is where things get a little tricky. So just, make sure you're paying attention and just writing everything down. And especially if you have, questions, rewatch this portion. And if you have any more questions, definitely ask in, either in the comments or on Discord, right? Really work this out, because I feel like this is one of the places where people start to really get a little confused with how to think about how things react. Okay, so carboxylic acids, as I mentioned, right? In the synthesis of carboxylic acids, it's really formed from the most oxidized thing, right? So the most possibly oxidized thing. Oh, actually, before we get into reductions, I realize there's actually one more amide reaction. There's one more amide reaction, and that is actually going to be amides particularly primary amides. So very important, this is primary amides reacting to make nitriles. Okay. And so you might be wondering why I'm including this one reaction here. It's because, remember, nitriles can form carboxylic acids. Okay, so we should kind of understand how to make these guys. And we know how to make amides, right? So you can imagine carboxylic acid, there's, a way, although it's a long way, right? I guess it's 2 arrows, so I'll just keep it 2 arrows, right? 2 arrows to get to the amide. And then the amide we can turn into a nitrile, which is going to be the last, and it's the non-traditional member of the acyl halide family. Okay, so why am I bringing up this guy out of nowhere? It might seem. Okay, well, if we look at the amide of the nitrile, notice how there's similar components. There's carbon and a nitrogen, carbon and a nitrogen. If I think about, what is really changing in this reaction, right? Like, let me change the colors here, actually. I like these better. So carbon and nitrogen, right? How am I changing the amide structure, right, to become the nitrile? Notice how the carbon nitrogen is retained and all I gain is 2 pi bonds. What do I get rid of? I get rid of the carbonyl and these 2 hydrogens. Well, wait a minute. That's an oxygen. So I'm getting rid of an oxygen and H2. I'm losing H2O again. So in the same way the anhydride, right, was a dehydration of a carboxylic acid, the dehydration of an amide will give me a nitrile. And so this is also going to be done with SOCl2. Okay. Now, you might remember that we talked about what is the basic site of a carboxylic acid, right? So what do you guys think is going to be the basic site of an amide? I think this one might be a little tricky. So think about it for a second, right? What do we think is going to be the basic site of an amide? Now, hopefully when you thought about this, you thought back to how carboxylic acids act as bases. They act as bases on their carbonyl, right? And I remember I showed you guys 2 ways to do this. You can either do it straight like this, or you can do it like this, where the oxygen resonates and then the pi bond attacks. It's really recognizing this part here that makes this problem a little bit easier, because I think a lot of you might have gotten stuck on the fact that nitrogen is so much more nucleophilic and basic than just an oxygen. So a lot of you might have thought to do this because, again, nitrogen attacking proton makes sense. We just said nitrogens are, very basic. But remember that this group here can also resonate with the pi bond. It's an atom with electrons and it's next to a pi bond. So this nitrogen could potentially just resonate into the carbonyl. And what we get is this resonance form here. And this resonance form might help us understand that, hey, this nitrogen actually donates quite a bit into the carbonyl, and really the electrons are localized on the oxygen. So even though the system looks different, we're going to do exactly the same thing we've been doing before, where we attack with the carbonyl oxygen, right? Whenever we, do this reaction, okay, or any reaction with these guys that requires a protonation or requires a Lewis base Lewis acid interaction. Okay, so I've given you the first step here. I want you to look at the reaction with SOCl2 and carboxylic acid, and I want you to try this on your own, okay? Because on the exam, you might be given a mechanism you weren't directly taught in class, but it correlates to another mechanism you've already seen, okay? So go ahead and try this out. It's going to be hard. Don't worry. Just try it out. So hopefully you guys paused and tried it. If not, it's okay. I understand this is a very tough thing to do, right? And a very tough thing to ask you guys. So don't worry. But as I said, we've kind of given you guys the first step here. I'm actually going to do it my way. Let's do it my way. So we can do this into this. And what results is this structure here. Now imagine for those of you that try this on your own, up to this part was probably fine. Even the next part too, because this comes down and kicks us off. That was probably very, very fine. It was probably this next part that really bothered you guys a lot, if it did, because this part here doesn't really have any intuitive sort of motion. Okay, there's no sort of intuitive motion here, because in the past, we've always done that the chlorine attacks here. Now, it's something that's impossible. It probably does eventually attack there. But think about how that serves any purpose, really, in continuing your product, because now you just have a chlorine on there. Again, you need to get rid of H2O. You don't need to add on a chlorine. So chlorine is not going to act as a nucleophile in this case. So what can chlorine then act as, right? If chlorine can't act as a nucleophile, then what is it going to do? Well, if you're stuck at this part, I'm going to ask you a question and maybe try it after asking this question. If chlorine can't act as a nucleophile, then what will it act as, right? Maybe even just generalize this to just some letter A with electrons. If letter A can't act as a nucleophile, then what can those electrons act as? Think about something we need to remove from this, right? We know we need to remove oxygen, and we've kind of already primed it for that, because remember, this here is a good leaving group. So we know that this needs to leave. So what can we take to prompt this system to leave? Okay, a bunch of questions there. So try it now if you were stuck here. And again, if you just want the answer, that's great too, right? But let's work through the logic here. If A is not going to act as the nucleophile, it's going to act as a base. And why was that important? Because remember, we have to get rid of two H's. And so maybe we get rid of this H here, and these electrons go to nitrogen. So that's one possible thing that could happen. Well, and you could, continue on from here, right? Because from here, you can just think, oh, right, this kind of looks like what we looked at before, right? When it looked like this. And you might realize what you need to do here, right? What you need to do here is the same cyclic movement we've done before, right? Where, remember, this would attack here, this would go here, and this would go here, right? It wasn't completely the same, right? Because there was no double bond here. It was a single bond before here, actually, right? So before there was a single bond here that did this reaction. But if we apply that same logic here, move this here, move this here, move this here, what you'll notice is that we make the nitrile, right? And we make SO2 and HCl, okay? So you can do that to figure out the end product there. That totally works, right? And if you're able to get to this point, good job, right? Another thing you can notice, and it's a little more clever, is that, well, wait a minute, hydrogen being taken away from a position beta to a leaving group. So this here is a leaving group. This carbon here is alpha, this nitrogen is beta. If I'm taking a beta hydrogen, what reaction can I do if I take a beta hydrogen? I could do a beta elimination. And you can actually have gotten to this point here. To be honest, whether this mechanism is the correct one, whether it isn't, who really cares? What matters here the most is that you understand how, we're using logic to get through this, right? So using any of these two mechanisms, I think is probably fine. I think this one is cooler just because of the intermolecular, but this one's even equally cool because it's pulling from old knowledge you've known before. You just have to have the courage to take either 1-2 path, okay? But even if you weren't able to do this on your own, that's totally okay, as long as you're building that chemical knowledge now of what to think about, right? How to apply older scenarios to these newer scenarios and make the nitrile. So yeah, pretty cool scenario there, right? Remember, the nitrile can be transformed into the carboxylic acid if you wanted to. It's the hydrolysis, but just wanted to show you how we can even get to the nitrile if we had to get to it. Because you can't just get from directly the acid to the nitrile. It has to be through the amide. Also, notice how we really did need 2 protons to get to the nitrile, so it has to be primary. Do not use anything that's not primary to do this reaction. Cool. So now that we've done that, we can get back to reductions. Okay. And so again, with reductions, what we were mentioning was, hey, right, we know that the carboxylic acid is the most oxidized form, right, of an alcohol. So a reduction would just kind of be the opposite process. And I don't really want to say it's reversible, so I'm gonna do this, but we know that this does Jones, and something will do this here, right? In the past, right, let's say we had like an aldehyde or a ketone, which was previously used, right, carbonyls. How do we reduce these guys into alcohols? We used lithium aluminum hydride and we use sodium borohydride, right? So we basically used a hydride system to reduce them. So we can probably do the same thing here, right? Just use a hydride system. So let's consider the reaction with lithium aluminum hydride. And one thing I want you guys to remember is that lithium aluminum hydride has to be kept away from water. Why might lithium aluminum hydride need to be kept away from water? Why might that be the case? So if you don't remember, it's okay. It's because lithium aluminum hydride is so basic. It's so reactive, so basic. It will react with water in an acid base before it reacts with anything else. Well, wait a minute. If lithium aluminum hydride will do an acid base before it does anything else, was there some kind of, so this is here is a base, right? Is there any acid component to this we need to be concerned about? The answer is we're concerned about this reaction here. Oh no, yikes, that is terrible. And so one of the very first things that's going to happen is lithium aluminum hydride will actually attack, the hydride will actually attack the proton. And what will form is that carboxylate that we talked about before. Now, if you remember what I said is that not many things can destroy this. Well, basically nothing can, but there is one person that is strong enough to do it. And it's actually going to be lithium aluminum hydride. So most nucleophiles will get to this point. I would even argue that sodium borohydride probably gets to this point. I'd have to check though. I'm not sure on the literature on this, but I'm pretty sure sodium borohydride gets to this point. But sodium borohydride is so weak, I don't think it would react any further. So I think it would stop here. But lithium aluminum hydride can continue to react further. And let's just see how it does that. So it's the one thing that can react to destroy this. So that's what it'll do, right? It's going to react to destroy that pi bond there. That's so hard to destroy. Lithium hydride can basically destroy any double bond, any XY double bond where X and Y are not the same atom. The stronger the dipole, the stronger lithium aluminum hydride reacts. Okay, so the stronger this dipole here, this here is a double bond. I'm not saying X equals Y, it's X double bond Y. The stronger this double bond, the more likely it is to react. Okay, it's just super strong. And what we're going to get is this dianion here, although it's not a naked dianion. Okay, it's sort of captured in this, by these two metals, right? But when we get to this point here, remember, if there is an O minus, right, there is the potential for minus to come down and kick off a group. It turns out that this oxygen here on the aluminum is actually a pretty good leaving group. And so what we're going to get is this here. Okay. Oh, lithium, aluminum, dihydroxide or something. I don't know. Okay. And so where did this H come from? That was the H that attacked, right? The H that attacked. This is just an aldehyde, right? Remember, aldehyde is just going to get attacked by the hydride. So now there's two of these. That water wash will cap pretty much all these protons. To make this alcohol here. Okay, so carboxylic acid can be destroyed by lithium hydride, but not really by anything else. And if we think about any other basic nucleophile that was known to do reductions, there was another one too, right? Grignard reagents. Grignard reagents was another thing that we could use. And so again, Grignard being so basic, it is just going to attack that proton, right? You can imagine the same thing for RLI as well. And what it's going to form is the carboxylate, either with the MgBr or with Li here, really, right? Like either, it's going to be either MgBr or Li there. Now, one thing I want you guys to understand here is that lithium aluminum hydride, right? 1 unit of hydride, of lithium aluminum hydride has 4 hydrides on it, right? Like lithium aluminum hydride has 4 hydrides on it, right? So theoretically, 1 unit of lithium aluminum hydride is enough to do the complete reduction, right? We only need 3 equivalents, 1 to deprotonate, 1 to attack, and then 1 to attack again, and then we're done, right? We only really need 3 of these equivalents. So 1 lithium hydride can kind of get the job done. Another way to think about it is that technically speaking, 1 EQ lithium aluminum hydride is really 4 EQ because there's 4 of these hydrides hidden in that 1 equivalent. So even if I tried to limit this reaction, like let's say I try to do 1 equivalent so that it only reacted with the aldehyde, it wouldn't work because technically 1 EQ is 4 EQ and all 4 EQs are just going to react, right? That's kind of how it works. So When we compare that to RMGBr RLI, who only have one reducing group on it, this has 4 groups, R is only 1 group, one equivalent of MGBR and RLI are truly just one equivalent, right? Only one equivalent of RLI is one equivalent of RLI. It's not like one equivalent of lithium aluminum hydride, which is really 4 equivalents. It's only one. So if we try to limit this reaction, it would limit, and it would limit to this, okay? And it's part of the reason why Nassiri asks 1EQ level questions, is because she wants to see what you think about, when one thing is reacting. Now, if we were to do this reaction in excess of either of these R reagents, right? M just means metal, so either one of these 2 metals, doesn't matter. This is going to be a topic of discussion depending on Nassiri. So when Nassiri says, I would highly recommend go to office hours, only one of you needs to go and then put it in the Discord or in the community chat board, right? To tell everyone what she thinks. If you look on the internet, you're going to get a wild variety of answers, especially concerning organolithiums. Some people consider organolithiums basic enough to, like, almost as strong as a hydride, lithium aluminum hydride, to destroy the carbonyl. But it's not enough to do, it's really complicated is what I'm trying to get at. And so maybe Nassiri doesn't want you to worry about that level. But again, it's going to be up to her whether she thinks one of these 2 can reduce. I've seen arguments for, Grignard never reducing past, this point here. I've seen arguments for organolithiums reducing past, this here, but going to a product that we're probably not expecting. It really depends, again, who you ask. So do yourself the good fortune of, at least one of you go and ask Nassiri what she thinks, and then just report it to the whole class. Hey, let me know too. Put it down in the comments. What does she say? Right? I want to know, right? Because I've never really asked her. I never really thought to ask her. Didn't really think it mattered. Okay, but these are what we expect for reductions. It is pretty hard to get a carboxylic acid down to an aldehyde. Mainly because things that can attack a carboxylic acid to reduce it are strong enough to also reduce aldehydes. So I would not try to access the aldehyde from the carboxylic acid, but you will learn of other derivatives. So let me put it this way. If the carboxylic acid is giving you trouble to get to something, you can just turn it into something else and then turn that thing into what you want. So we can turn the carboxylic acid into something else that gives us the aldehyde easier. Same thing with ketones too, actually. I'll just tell you here, nitriles are actually really good ketone reagents. So if you ever need if you ever need to make a ketone, nitrile is probably the way you want to go. Acyl halide actually also works too, as we'll see in the next video. Acyl halides work wonders as well. Okay, but that's typically when we think of reductions to like ketone and aldehyde, we don't go through the carboxylic acid, because carboxylic acid, anything that will reduce that will reduce the ketone or the aldehyde. So there's no point in doing it directly. You have to do it indirectly. Cool. So now that that's sort of out of the way, oh, I guess there's one more reducing agent you could use too. So if nucleophilic reducing agents are kind of an issue, we can use electrophilic reducing agents, specifically borane. Borane is you might remember that from 118B, right? This reaction begins with oxygen attacking the borane. So instead of, reducing agent attacking the acid, borane gets attacked by the acid, which is kind of interesting, right? But this will actually also reduce down. Don't worry about the mechanism, is super crazy. To be honest, I really don't want to explain it because sometimes I get lost too. If you really care, you can look it up, but I don't think Nassiri teaches the mechanism for this anymore. It's just a good one to keep in your pocket. But because this is an electrophilic reagent, one thing to think about is that for chapter 20, right, electrophilic means that we need a very strong nucleophilic oxygen. So not very many things can actually be reduced by borane. Carboxylic acid is one of those things. And there's one other thing, really, two other things that can kind of be reduced by borane, but I thought I'd just throw it in there just for fun. Cool. So that leaves us with one final reaction. So already we got her so quickly, didn't we? Took us barely any time to get to this point. I'm only joking. But there is one more reaction we can do with carboxylic acids that have some utility, and that is going to be the HVZ reaction. So what is HVZ, right? HVZ is the transformation of carboxylic acids into alpha bromo carboxylic acids. Okay, and so you might be thinking, oh, wait a minute, we've kind of seen this before, right? When we had a ketone or an aldehyde and we needed to do a bromination, especially a monobromination like this one, right? What did we do? We just added in Br2 and H3O plus, right? Now, to understand why we can't just do this process, right? Because actually what this is going to be is phosphorus and Br2, right? Is to remember that the intermediate for this was an enol, right? Or an enolate if you're doing in basic solution, right? This was the intermediate of the reaction. Now, normally to make the enol or the enolate, right, we would have to use like a base of some sort or like an acid. But remember that if I use the base, let's say, one good one was LDA, right? Well, the first thing that's going to happen, right, strong base, where's that going to react? It's going to react here, right? So you're first going to form this guy here. The carboxylate is so stable, again, doesn't really want to react with anything. Although you could force this if you put in 2 more equivalents of LDA. If you really wanted to, you could force it. And what that forms is this dienolate here, right? Because there's 2, or no, it's just gonna be so hard to say. It's gonna be some kind of endiolate ion, right? Because it's a diol, not a dienol. Dienol wouldn't make sense because that would be 2 alkenes. Pedantic argument. Don't worry about that. But you can form this here. But I mean, it's really hard to do this, right? Like once you've deprotonated once, it's like sufficient. I mean, you need 2 equivalents to accomplish this, really, from what I've read. So to form this enol is very hard, not very practical, right? And again, there's other things that form it better. So we could just do, use other things really if we had to. But the basic enol, not a very good reaction to use. The acidic enol actually is not too shabby. So what I mean by this is, forming this guy here actually isn't too bad. And I've actually forgot, what was it again? Sorry, it's late. I'll have to look this up. But I know that you can do this a lot easier with acid than you can with I'll have to look this up. The thing is, if I do it now, it might take me a while. Okay, I will try to find this, but I know that the enol is a way more accessible reaction than the enolate. And I forgot I think they use like TMS or something to do it. I think you use TMS. So what that means then is that one of these guys are probably TMS protected. You probably don't even recognize this, so it's okay. So don't worry about it. But carboxylic acids and enols made from carboxylic acids a little bit easier. But here's the thing: if this were easy, then what's the point of teaching you HVZ? What I want you guys to realize is essentially, I want you guys to think of these things as nearly impossible or just really hard, right? I want you to think of these as really, really hard. Because if they're really hard, then it explains why we need HVZ as an answer, right? Otherwise, we could just, if one of these were easy enough, we could just use one of these and just do the reaction we wanted to. So for the series class, just treat this as nearly hard or essentially impossible to do, okay? And so that's why we need to do the HVZ. Now, if you've seen the HVZ reaction, you know that it's very complex and kind of non-intuitive. But the thing is that we can break it into segments to help us understand how the reaction works and make it more digestible and easier to understand. And again, with going into closed note in-person exams, we can no longer rely on our notes. Before I would just say, just write it down if it comes up, but we can't do that anymore. We can't just write it down, right? We've got to we got to go ahead and learn how to logic our way through any of these reactions. Okay, so let's go ahead and let's break this reaction down. And the first part is very simple. We are doing the carboxylic acid to the acyl bromide. Okay, so we learned the acyl chloride earlier, right? We learned how to use SOCl2. Well, this reaction here is going to use PBr3 instead, because before, right, I wrote what phosphorus and Br2. Phosphorus, Br2 make PBr3. And PBr3, you might remember, is just like SOCl2 in that it converts the alcohol into a bromide. So how do we do it? I mean, we're going to do exactly the same thing we've done before, right? Just a slightly different chemistry. If I remember correctly, because there is no carbonyl sink like in SOCl2, you can actually kick off a bromine immediately because that's the best thing to take the electrons. If there was a carbonyl, that'd be better, but there is no carbonyl. But that's okay because it actually helps us out a lot if there is no carbonyl, because then bromine can just attack here instead of having to do like a leaving group step. And what we get is this here. Okay, and once again, we can kind of just do our ring around the rosy here. And what results from this is the acyl bromide. Okay, acyl bromide. And so the first step, again, makes the acyl bromide just by the reagent. So why might we want to do this? Well, remember how back here we said that the carbonyl or the carboxylic acid really just can't make an enolate? Well, acyl halides and bromides, really, right? These guys are actually the most analyzable derivative out there. So the reason why we turned into an acyl halide is because we can analyze this very easy. Okay, and so if the issue before was that we had an OH that prevented analyzation from occurring easily, then get rid of it. Turn it into something that can't, give up a proton or cause issues, and analyze that thing. So that's what the first step achieves. It makes a better analyzable component. So better analyzable, this guy. And then we're going to just go ahead and analyze. Now, just a quick note here, right? This reaction here forms PBr2O, and this will continue to react about 2 more times to create I think I moved my electrons wrong somewhere. So I think I moved my electrons wrong here, but that's totally fine. Just look in your notes how she does it then. Essentially what needs to happen here, there should be an H here. So where am I missing? Oh, no. Okay, I see what I did wrong. Okay. So there's going to be an H on here, and then something will pick it up. Probably the POBR2 leaving group, right? It's going to pick up that proton. And this will eventually turn into H3PO3. Okay, so OH is added for every BR. So we can get to H3PO3, which is a, hopefully a recognizable acid. And that recognizable acid is going to give a proton, the acyl bromide. We're basically doing an acidic enolization. H2PO3 minus, we'll just take that proton. And what will form is this here, right? That more analyzable compound, right? The bromine. And again, no issues, right? No real issues here because we don't have that OH here. So that's great. That's great news. It's great news that we're at this point. Now, how do we normally do, how do we normally, add halogens on the alpha position? We just do an attack, right? This is where we're doing the preparation of that alpha bromide. Okay. So we did an enol type attack. And that enol type attack was on that Br2. Something in solution, maybe that Br minus H form will pick up the proton. But now we have our alpha bromo acyl bromide. So these 3 steps I think are the most intuitive out of the total number of steps. Right, it's the easiest to understand, I think. And it's not that the next part isn't easy to understand. It's just like, you have to think a little bit about where things go because we still have to get to that O part there. But, again, as long as we logic our way through it, we'll probably have a better time than we would have normally. Now, I just want you to recognize, right, what we're essentially doing here. All we're really doing is we're switching Br into O. So when we go back here and look at the components of the reaction, where is that O going to come from? So look at our components of the reaction. What is the only thing that has O? The only thing that has an oxygen is the carboxylic acid. So that means that if we want to add an oxygen to where the bromine is, then we have to add a carboxylic acid to the acyl bromide. And that shouldn't be impossible because we learned that carboxylic acids like to add to acyl bromides, right? That's what we learned all the way back here. Not all the way back here, but right here, right? If I did SOCl2, that turns this into Cl, and the carboxylic acid can easily attack that center. So that's going to be the first thing that we're going to do here. And I've seen this done a couple of ways. I've seen this done where the carboxylic acid protonates this bromo, the acyl bromide. I've seen it done where the carboxylic acid just attacks it. I would say it's really up to you how you want to do it, or I mean, really not to you. Just do what it does in the notes. I'm just going to do it the protonated way because it just makes a better nucleophile. So what I mean is, oh, actually, I realized if we don't do this, actually, if we keep this here, so let's say that something doesn't pick up the proton, we can actually start from this. So we can be a little clever here. Okay. And then carboxylic acid can go ahead and attack. So it's going to make some kind of like anhydride here, essentially, or the formings of an anhydride. Okay. Oh, better to do this. Remember, always better to do that. Now bear with me here. Things are going to get a little messy. This is the alpha bromo part. Right? And then this here is going to be the carboxylic acid that just attacked. Okay, so now we have that oxygen there, right? So we've prepped the oxygen. The other thing that we need to do here is get rid of this bromine. So not only do we need to put an oxygen here, but the bromine needs to leave. And the best way to do that is just kick it off, right? It's a great leaving group. So this can come down and kick this guy off. This guy is probably going to fall off first. So I would take off that proton first and then kick this guy off. Okay, actually, let's do it this way. Let's still segment into steps. So 5. So we added those two together. The next thing we're going to do is go from here to here. Right, so this is basically forming the anhydride, right, to form the anhydride, and basically gets off that bromine too, right, because we don't need this bromine anymore. So electrons here come down, kick off bromine, and we get to here. Now, again, we've essentially done the two most important things. We got rid of bromine and we've added the oxygen to that center, right? The oxygen we need to make this an alpha bromo acid. Okay, so what do we need to do rest? Well, now we just have to get rid of this whole group here, right? That needs to go bye-bye, right? And really the only way to do that is to activate it for attack, right? So this last part I'm going to just kind of smush in with here too, just for the sake of time, but I can activate this for attack. Get, remember that bromine that I left earlier, right? Get that guy on there. And now, right, when I have this oxygen group here, these electrons can come down. Instead of kicking off bromine, because doing that will make us go backwards, we can kick off this whole group, right? We can kick off this whole group just like that. And by doing that, that gives us a carboxylate that will definitely pick up a proton in solution. And an acyl bromide, just like that. Oh, actually, this guy can just pick up this proton here. Okay, and what we end up with is our final product. The alpha bromo acid and an acyl bromide. This acyl bromide will go back to step 2 and keep going. So this is not going to be a product because this is just going to be consumed. So again, let's just walk through this really quickly so that we understand the components and know how to break it down so that when we're on the exam, we don't freak out when we see this as a mechanism question, right? So first off, right, analyzing or halogenating carbonyls used to go through an enol intermediate, but enols are really hard to make on carboxylic acids just because of this annoying OH group here that always ionizes first, right? And this reaction is a little accessible, but we're gonna have to treat it like it's not because then otherwise HVZ is kind of doesn't make sense to do, right? So whole point here is that analyzation of a carboxylic acid is not really gonna work. So what do? We turn the carboxylic acid into something that can analyze, and we turn it into the best analyzable group, right? Acyl halides, best analyzable group. Just do what we done very first reaction we learned: carboxylic acid, acyl halide, turn it into that. Then we analyze that acyl halide, and we do the attack that we're familiar with from 118b, right? Just use the enol to attack Br2 so that we get our alpha bromination. Now that we've gone to the alpha bromo part, right? All we have to do now is replace, right? All we have to do now is replace the bromine here for an OH, and we'll have our intended final product, right? We can see that there's just an OH here now. The only thing in solution with an oxygen is the carboxylic acid. So the carboxylic acid has to be the thing that attacks the alpha bromo, and that's okay because we've seen that, right, to make anhydrides. So essentially what we're doing is when we add this on, we form an anhydride. Now, once we have this anhydride, we've prepped that oxygen that we need to make the alpha bromo acid. And now we just have to get rid of this group. So how do we do that? We activate it for attack. Bromine attacks it. And when oxygen comes down, right, to make the carbonyl again, we just kick off the group that we need isolated as the leaving group, and we get our final product. So that's just the way that I think about it. It helps me really segment everything and figure everything out. And hopefully that can help you too. I think really with HVZ, you just got to keep writing it out until it's like glued in your brain. Now, really the purpose of HVZ is that not only does it give us access to something that technically should be impossible, but it also gives us access to SN2s that we normally wouldn't have. So this one here takes 3 days, but we can do this here. This actually is going to be zwitterion. This is an amino acid. I just made glycine here. So you can imagine why HVZ was important back in the days, because we can make amino acids. So alpha amino acids. For the final, you will learn how to do a lot of this stuff. We can also react with NaOH H2O. I forget how long this takes because this also has an acid base, but it will basically do this here. Basically, any sort of nucleophile you can think of can replace here. NaCN is a good one because what you get is a nitrile here, and you can actually turn that into a carboxylic acid, right, with hydrolysis. So you can do that. You can actually turn this into, you can do Jones with this. So there's 2 different ways to make 2 different kinds of carboxylic acids, alpha diacids or beta diacids. This here is a beta diacid. Right, so a little cool thing there. Point is that if we think about this from that same standpoint as we did before, right? If we think about this as a pi bond here, remember that the SN2, oh, sorry. You might remember that in allylic bromides, the SN2 was very stabilized because the p orbitals here would stabilize the transition state that looked like a p orbital in SN2. Same thing here. These p orbitals here are just going to stabilize that there. Okay, so the SN2 is a pretty good reaction, but it takes quite a while. They're not the best reactions, but they give us access to them, that's pretty dope. Okay, cool. Well, that should be it for chapter 19. This is longer than I wanted it to be, but it's okay. If there are any questions, please let me know. If you think there's a mistake, please let me know. As always, just write a comment or email me. Some of you guys know my email. In case you don't, here it is. Okay, this is ucdavis.edu. Yeah, cool. Good luck. I'll have the next video up soon. Good night, guys.